At first glance, the fields of artificial intelligence, machine learning, and data science can feel like an overwhelming collection of disparate algorithms, specialized libraries, and complex architectures. However, beneath the surface of every predictive system, from simple spreadsheet forecasts to the most advanced neural networks, lies a single unifying framework known as statistical learning. Statistical learning is not merely a collection of tools. It is a mathematical philosophy that allows us to model the underlying structures of the world by separating meaningful patterns from random noise. If you can master this fundamental philosophy, you will no longer see machine learning as a series of black boxes to be connected blindly. Instead, you will begin to think like an architect, understanding exactly why models behave the way they do, where their limits lie, and how to debug them when they fail in production. To build a solid mental model of statistical learning, let us start by defining the primary goal. We live in a world filled with observable data, which we can split into two categories: the things we want to predict or understand, and the measurements we use to make those predictions. In the language of statistics, the variable we wish to predict is called the response variable or the dependent variable, and we denote it with the capital letter Y. The measurements we use to make this prediction are called predictors, independent variables, or features, and we represent them as a set of variables from x1 to xp, which we can group together into a single multidimensional vector called x. Our fundamental assumption is that there is some systematic relationship between our input features x and our output response y. We express this relationship mathematically by stating that y is equal to a function of x, plus an error term represented by the Greek letter epsilon. Let us break down this equation, as it is the foundation of everything that follows. The function f represents the systematic information that x provides about y. It is the underlying truth, the physical law, or the consumer behavior pattern that we are trying to uncover. Epsilon represents the random error term. This error term is critical because it represents all the things we cannot measure, the inherent randomness of the universe, or the minor variables that we chose to omit from our model. By definition, epsilon is completely independent of our inputs x, and it has an average value of 0. This means that if we were to observe the same inputs x thousands of times under identical conditions, the output y would fluctuate slightly due to epsilon, but these fluctuations would cancel each other out on average. To visualize this spatially, imagine a two-dimensional graph where the horizontal axis represents the number of hours a student studies, and the vertical axis represents their exam score. If we plot data points for hundreds of students, we will not see a perfectly clean line. Instead, we will see a cloud of points that generally slopes upward. The systematic function f represents a smooth curve running right through the center of this cloud, capturing the general trend that more studying leads to higher scores. Epsilon represents the vertical distance between any individual student's data point and that smooth curve. One student might have slept poorly the night before the exam, causing their score to drop below the curve, while another student might have guessed several multiple-choice questions correctly, pushing their score above the curve. The curve itself represents the systematic signal, while the deviations from the curve represent the noise. When we build a machine learning model, we do not know the true function f. We only have access to a set of historical observations, which we call training data, and we use this data to estimate a function that we call f hat. The goal is to make f hat as close to the true function f as possible. This brings us to a crucial distinction. Why do we want to estimate this function in the first place? In practice, our goals generally fall into one of two categories: prediction or inference. Understanding the difference between prediction and inference is one of the most important steps in designing an effective machine learning system. In a prediction scenario, we have access to the inputs X, but the output Y is unknown or has not happened yet. For example, we might want to predict whether a customer will churn next month based on their usage patterns today. In this case, we are not particularly interested in the mathematical structure of our estimated function f hat. We do not necessarily care if the relationship is linear, exponential, or highly complex. Our primary objective is simply to produce the most accurate prediction possible, which we represent as y hat. The quality of our prediction depends on two types of errors: reducible error and irreducible error. Reducible error is the portion of the prediction error that we can minimize by choosing a better model, gathering more training data, or engineering better features. It exists because our estimated function f hat is not a perfect match for the true function f. Irreducible error, on the other hand, is the error introduced by the random term epsilon. Because epsilon is independent of x, we cannot predict it using our input features, no matter how complex our model is or how much data we collect. Irreducible error acts as an absolute physical limit on the accuracy of our predictions. Imagine trying to predict the exact arrival time of a flight. You can build a highly sophisticated model using wind speeds, air traffic, and departure delays, which reduces your reducible error. However, a sudden, unpredictable gust of wind or a minor mechanical check at the gate will always introduce random variations that you cannot forecast. That randomness is the irreducible error, and accepting its existence prevents us from chasing impossible levels of accuracy. In an inference scenario, our objective is entirely different. We are not using our model to predict future values of y. Instead, we want to understand the exact nature of the relationship between x and y. We want to know which individual features are associated with the response, whether the relationship is positive or negative, and whether the effect of one feature depends on the value of another. For example, a medical researcher might want to know how different dosages of a drug affect patient recovery time. In this case, we cannot treat our estimated function f hat as a black box. We need to be able to look inside it, understand its structure, and interpret its coefficients. If we use a highly complex, nonlinear model like a deep neural network, we might achieve high predictive accuracy, but we will lose the ability to perform inference because we cannot easily explain how each feature contributes to the final output. This tension between prediction and inference leads directly to our first major engineering design decision: the choice between parametric and non-parametric estimation methods. When we decide how to estimate our function f hat, we are choosing how much structure we want to impose on our model. This decision has massive implications for memory footprints, latency constraints, compute costs, and the interpretability of our system. Parametric methods simplify the problem of estimating f hat by making an assumption about its functional form. A classic example is a linear model, where we assume that the relationship between our inputs and our output is a straight line or a flat plane in higher dimensions. Once we assume a functional form, the task of estimating f hat reduces from trying to find an arbitrary, infinitely flexible mathematical function to simply finding a set of numerical weights or parameters. Spatially, this is equivalent to taking a rigid, flat sheet of metal and tilting it until it fits as close as possible to our cloud of data points. The engineering advantages of parametric models are profound. First, they require an extremely small memory footprint. Once a linear model is trained, you do not need to keep the training data in memory. You only need to store the estimated parameters, which might be just a few floating point numbers. Second, the computational cost at inference time is virtually non-existent. To make a prediction for a new data point, the model simply performs a dot product between the input feature vector and the parameter vector, which takes a fraction of a microsecond. This makes parametric models ideal for high-throughput, low-latency environments, such as real-time advertising bidding engines, where predictions must be made in milliseconds. However, the primary drawback of parametric models is high bias. If our assumption about the shape of the true function f is wrong, for instance, if the true relationship is highly curved rather than linear, our model will never be able to capture that curvature no matter how much data we feed it. Non-parametric methods, conversely, do not make any explicit assumptions about the functional form of f hat. Instead, they seek to estimate f by fitting a curve that gets as close to the training data points as possible without being constrained by a rigid shape. A classic non-parametric approach is k-nearest neighbors, where the prediction for a new data point is simply the average of the outputs of the k closest points in the training dataset. Spatially, instead of fitting a rigid sheet of metal, a non-parametric model is like a highly flexible, elastic fabric that bends and stretches to touch or pass near every individual data point. While non-parametric models can capture highly complex, nonlinear relationships that a parametric model would completely miss, they come with steep engineering trade-offs. Because they do not simplify the model into a fixed set of parameters, they must store the training data, or a highly detailed representation of it, in memory to make future predictions. This leads to a massive memory footprint that scales with the size of the training dataset. Furthermore, the compute cost during inference is high. For k-nearest neighbors, the model must calculate the distance between the new input and every single point in the training set, which can result in unacceptable latency as the dataset grows. Additionally, non-parametric models are highly susceptible to overfitting, meaning they can become so flexible that they end up fitting the random noise represented by epsilon rather than the systematic signal represented by f. When this happens, the model performs exceptionally well on the training data but fails completely on new, unseen data. To see these concepts in action, let us walk through a production case study involving an e-commerce platform that wants to estimate customer lifetime value, which we refer to as LTV. The platform wants to use historical customer data, such as the total number of purchases, the average order value, the customer's age, and the channel through which they were acquired, to estimate how much revenue a new customer will generate over their first year. In this scenario, the engineering team faces a dual requirement from the business. The marketing department needs to perform inference. They want to know which acquisition channels are driving the highest value customers so they can allocate their advertising budget effectively. They need to know if a dollar spent on search engine marketing yields a higher return than a dollar spent on social media campaigns. For this inference task, the team chooses a parametric linear regression model. The model is highly interpretable. The coefficients directly tell the marketing team the average increase in LTV associated with each acquisition channel, holding all other variables constant. The compute cost is negligible, and the model can be easily integrated into a real-time marketing dashboard. At the same time, the finance department needs raw prediction accuracy to forecast company revenue for the upcoming quarters. They do not care about the individual impact of each acquisition channel. They simply need the most accurate LTV predictions possible for their financial models. For this prediction task, the engineering team builds a non-parametric gradient-boosted tree model. This model can capture complex, nonlinear interactions, such as the fact that younger customers who purchase through mobile apps have a completely different spending trajectory than older customers who purchase through desktop browsers. Because this model is non-parametric, it requires significantly more memory and compute to run, but the increased predictive accuracy translates directly into more precise financial forecasts, justifying the added operational costs. When deploying statistical learning systems to production, engineers must be prepared to debug and troubleshoot a variety of unique failure modes that do not occur in traditional software development. One of the most common and devastating issues is data leakage. Data leakage occurs when information from the target variable y is inadvertently included in the input features x during the training process. This creates an artificial scenario where the model appears to have an incredibly low reducible error during offline testing, but performs horribly once deployed to production. For example, suppose you are building a model to predict whether a user will sign up for a premium subscription. If your training dataset includes a feature that records whether a user visited the premium checkout confirmation page, the model will quickly learn that visiting this page is a near-perfect predictor of subscription. However, in production, the model is expected to predict subscription intent before the user reaches the checkout page. Since the confirmation page feature will be empty at the moment of prediction, the model's performance will collapse. To debug and prevent data leakage, engineers must establish strict boundary lines between the historical window used to construct features and the future window used to define the target variable. You must ensure that no feature contains information that would be unavailable at the exact millisecond the prediction is requested. Another critical production challenge is prior probability shift and concept drift, which occur when the relationship between your features and your target changes over time. In our mathematical framework, this means the true function f or the distribution of the inputs x is shifting. For instance, if an e-commerce platform undergoes a major redesign, or if consumer behavior changes due to an economic downturn, the historical patterns captured by f hat will no longer match the new reality. To monitor and debug these shifts in production, you cannot simply look at application crash logs, because the model will continue to output predictions without throwing errors. Instead, you must monitor the statistical properties of the model's inputs and outputs. By logging all predictions and comparing them to the actual outcomes as they arrive, you can track the model's residuals over time. The residual is the difference between the true output y and the predicted output y hat, which represents our estimate of the error term. If your model is performing correctly, the average of these residuals should hover close to zero, and they should look like random noise. If you notice that the average residual is consistently positive or negative, or if the variance of the residuals begins to spike, it is a clear signal that the underlying function has shifted, and the model must be retrained on more recent data. By building robust telemetry around feature distributions and residual metrics, you can ensure that your statistical learning models remain reliable long after their initial deployment. To expand our understanding of how statistical models interact with the world, we must examine the nature of the data we feed them. In our previous discussion, we assumed that every historical observation consisted of both an input feature vector x and a corresponding ground truth output y. While this is the most common setup in applied machine learning, it is by no means the only one. Depending on whether we have access to target labels, or if we must learn through direct interaction with an active environment, we divide the machine learning universe into three distinct paradigms: supervised learning, unsupervised learning, and reinforcement learning. Each paradigm represents a fundamentally different way of formulating mathematical problems, and each imposes its own set of engineering constraints, computational challenges, and production realities. Let us begin with supervised learning, which is the direct extension of our y equals f of x framework. In this paradigm, every single data point in our training set is a paired observation consisting of a feature vector and a corresponding response label. The presence of this target label is the defining characteristic of supervised learning. Spatially, you can visualize supervised learning as a mapping problem. If we are trying to predict house prices, our features might represent spatial coordinates on a two-dimensional grid, along with additional dimensions for square footage and number of rooms. The target label represents a height value at each coordinate. Our model's goal is to fit a smooth, multi-dimensional surface that passes as close as possible to these height values. Because we have access to the actual height for every point in our training set, we can explicitly calculate the error for any prediction we make. We can measure the distance between our estimated surface and the true height, and use this mathematical feedback to tilt, bend, or warp our model until the prediction error is minimized. Supervised learning problems are further split into regression and classification based on the nature of the target variable. If the target is a continuous numerical value, such as a salary or a temperature, we are dealing with a regression problem. If the target is a discrete categorical label, such as classifying an email as spam or not spam, we are dealing with a classification problem. In classification, instead of fitting a continuous surface that predicts height, our model seeks to construct a decision boundary, a multidimensional wall that separates points belonging to different classes. Spatially, if we have blue points representing spam emails and red points representing legitimate emails plotted in a high-dimensional space, the classification model's task is to draw a clean boundary sheet between the red cloud and the blue cloud. Unsupervised learning represents a major departure from this framework. In an unsupervised scenario, we are presented with a dataset containing only input features x, with absolutely no corresponding target labels y. We have no ground truth, no height values to fit, and no predefined classes to separate. In the mathematical sense, we are no longer trying to predict a response variable. Instead, we are trying to understand the joint probability distribution of the inputs, or find interesting structures within the feature space itself. Spatially, instead of looking at a cloud of points with colors or heights and trying to fit a surface, we are looking at a uniform cloud of points in a high-dimensional space, and our goal is to describe how those points are organized. Because we lack target labels, we cannot calculate prediction errors in unsupervised learning. There is no simple loss function that tells us how close we are to the truth, because the truth is undefined. This makes unsupervised learning both highly flexible and notoriously difficult to evaluate. The two most common unsupervised tasks are clustering and dimensionality reduction. In clustering, we seek to partition the data points into distinct groups such that points within the same group are close to one another, while points in different groups are far apart. Spatially, this is like identifying separate, dense galaxies of stars within a dark void. In dimensionality reduction, our goal is to compress our high-dimensional space into a lower-dimensional representation while preserving as much of the original structural information as possible. Spatially, imagine a three-dimensional dataset where all the points happen to lie on a flat, tilted sheet of paper. By identifying the orientation of that sheet, we can project the three-dimensional coordinates onto a flat two-dimensional plane without losing any of the spatial relationships between the points. Reinforcement learning introduces a third paradigm that is fundamentally different from both supervised and unsupervised learning. In reinforcement learning, we do not start with a static, pre-collected dataset of observations. Instead, we have an active agent that interacts with a dynamic environment over a sequence of discrete time steps. At each step, the agent observes the current state of the environment, makes a decision to take a specific action, and receives a numerical reward or penalty from the environment, along with a transition to a new state. The goal of reinforcement learning is not to find a static mapping function, but to learn an optimal policy, a strategy that dictates which action to take in any given state to maximize the expected cumulative reward over the long term. Visualize reinforcement learning as a pilot learning to fly a helicopter. There is no static dataset showing the correct joystick movements for every gust of wind. Instead, the pilot makes a minor adjustment, the helicopter tilts, the wind pushes back, and the pilot receives immediate sensory feedback about the stability of the aircraft. The agent must balance exploration, which involves trying new actions to discover their consequences, with exploitation, which involves using actions that are already known to yield high rewards. This temporal feedback loop means that the agent's actions directly influence the future data it observes, creating a dynamic, non-stationary data stream that violates the traditional statistical assumption that our observations are independent and identically distributed. Transitioning from theory to engineering design decisions reveals that each paradigm comes with distinct trade-offs that dictate when and how they should be deployed in production systems. For supervised learning, the primary engineering bottleneck is the data labeling process. While supervised algorithms are highly mature and can achieve remarkable accuracy, they are entirely dependent on having access to large volumes of high-quality, labeled training data. In the real world, obtaining these labels is often incredibly expensive and time-consuming. You may need to hire teams of human annotators to review images, label medical scans, or categorize text documents. This creates a severe cold start problem. You cannot train your model until you have labels, but you cannot justify the cost of labeling until you prove the model's value. To mitigate this labeling bottleneck, engineers often look to unsupervised learning as a pre-processing step. Because unsupervised models do not require labels, they can run on cheap, raw data streams that are collected automatically. For instance, you can use unsupervised dimensionality reduction, such as principal component analysis or autoencoders, to compress massive, noisy raw datasets into compact, dense feature representations. By doing this, you drastically simplify the feature space, allowing you to train subsequent supervised models with far fewer labeled examples. However, the trade-off is computational complexity. Unsupervised algorithms, particularly clustering methods like hierarchical clustering, often have quadratic time complexity with respect to the number of data points. This means that running them on large-scale production databases can require massive compute clusters and long execution times, whereas supervised models can often be trained incrementally or on smaller, representative subsets. Reinforcement learning presents a completely different set of engineering challenges, primarily centered around sample inefficiency and simulator fidelity. Because a reinforcement learning agent must learn through trial and error, it often requires millions of interactions with the environment to discover an optimal policy. In physical systems such as robotics or autonomous driving, letting an untrained agent learn through real-world trial and error is impossible, as it would lead to physical destruction and safety hazards. Therefore, engineers must build highly detailed physics simulators where the agent can train safely at high speeds. This introduces the reality gap, the discrepancy between the simulator's simplified mathematical models and the messy physics of the real world. A policy that performs perfectly in a simulator might fail catastrophically in production because the simulator did not capture subtle details like friction variations, wind shear, or sensor noise. Furthermore, reinforcement learning systems suffer from feedback delays. Unlike supervised learning, where the model receives an immediate loss signal for every single prediction, a reinforcement learning agent might take hundreds of actions before receiving a non-zero reward, such as winning or losing a game of chess. This credit assignment problem makes training reinforcement learning systems highly unstable, requiring complex architectures and careful tuning of discount factors and exploration rates to prevent the policy from diverging. To see how these three paradigms converge within a single production ecosystem, let us study the architecture of a modern music recommendation engine. A streaming service must solve multiple complex problems to keep users engaged, and no single machine learning paradigm can handle all of them. Instead, the engineering team deploys a hybrid system where supervised, unsupervised, and reinforcement learning models run in parallel, passing data to one another to create a seamless user experience. The core of the music recommendation engine relies on unsupervised learning to map the vast catalog of millions of songs into a manageable latent space. Every track has raw audio features, such as tempo, energy, and key, along with behavioral features representing which users listen to which artists. The engineering team uses an unsupervised matrix factorization model, or a deep autoencoder, to compress these sparse, high-dimensional interaction matrices into low-dimensional song and user embeddings. These embeddings are coordinates in a continuous musical space where similar artists sit close together. By using unsupervised clustering on these embeddings, the system can automatically group songs into niche genres or moods without requiring human editors to manually tag every track. Once the music catalog is structured using unsupervised embeddings, the system uses supervised learning to handle immediate engagement predictions. When a user opens the application, the system must choose a set of candidate songs to display on their homepage. To do this, a supervised classification model is trained on historical listening logs. The features X represent the user's current context, such as the time of day, their device type, and their recent listening history, along with the embedding coordinates of a candidate song. The target Y is a binary label indicating whether the user listened to the song for at least 30 seconds without skipping. Because the platform logs billions of user interactions daily, they have a massive, continuous stream of labeled training data. The supervised model can quickly score thousands of candidate songs, filtering out tracks that have a high predicted skip probability. However, if the recommendation engine relied solely on supervised skip predictions, it would quickly fall into a feedback loop known as the filter bubble. The model would learn to recommend only the user's favorite tracks, resulting in a repetitive, stale experience that causes long-term user churn. To prevent this, the engineering team introduces a reinforcement learning layer at the top of the stack. The reinforcement learning agent's environment is the user's session. Its actions are the sequences of songs it chooses to play, and its reward is the total session duration. The agent learns a policy that balances exploitation, playing highly rated, familiar songs to get immediate positive rewards, with exploration, which involves playing new, unfamiliar genres to discover if the user's tastes are broader than currently known. By optimizing for the long-term cumulative reward of user retention rather than the immediate click-through rate of a single track, the reinforcement learning policy ensures a dynamic and engaging user experience. Debugging and monitoring a hybrid system of this scale requires engineers to be vigilant against paradigm-specific failure modes. In supervised learning, the most common silent failure is label noise. Label noise occurs when the target labels in your production logging are corrupted or misclassified. In our music recommendation case study, if a user falls asleep while listening, the system might log hours of continuous plays, marking those tracks as highly successful. However, these positive labels do not represent true preference. The supervised model will begin to train on this noisy data, corrupting its decision boundaries. To debug this, engineers must implement heuristic filters that detect and discard anomalous label events, such as flagging sessions with unusually long, uninterrupted playback times as sleep events, before they reach the training pipeline. In unsupervised learning, the primary failure mode is sensitivity to feature scaling and cluster instability. Because clustering algorithms rely on distance metrics in a high-dimensional space, features with larger numerical ranges will completely dominate the calculations. For example, if you cluster users based on their age, which ranges from 18 to 80, and their annual income in dollars, which ranges from 10,000 to 1 million, the distance calculations will be driven entirely by income. The age feature will be mathematically ignored. To debug this, engineers must enforce strict pre-processing pipelines that normalize all features to a common scale using standardization or min-max scaling. Furthermore, they must monitor cluster stability by periodically injecting minor noise into the feature space and verifying that the resulting cluster assignments remain consistent. If the clusters shift drastically with minor changes in the input, the clustering boundaries are too weak to be trusted in production. For reinforcement learning, the most notorious failure mode is reward hacking. Reward hacking occurs when the agent finds a loophole in the reward function that allows it to collect high rewards without actually solving the intended problem. In a recommendation system, if the reward function is defined purely as maximizing the click-through rate, the reinforcement learning agent will quickly learn to show extreme, sensationalized clickbait titles or thumbnails. This achieves the mathematical goal of maximizing clicks, but it destroys the user experience and damages the brand's reputation. To debug and prevent reward hacking, engineers must design multifaceted reward functions that incorporate countermetrics, such as user satisfaction ratings, return rates, and session completion metrics. They must also implement policy safety bounds, guardrails that restrict the agent's action space to prevent it from exploring highly erratic or harmful behaviors. By monitoring the discrepancy between simulated rewards and actual business outcomes, you can detect when your reinforcement learning agent is drifting toward unintended optimizations, ensuring the safety and alignment of your production systems. To expand our understanding of these paradigms in production, we must also consider the role of semi-supervised learning, which acts as a bridge between the supervised and unsupervised worlds. In semi-supervised learning, we are presented with a small set of labeled observations and a massive volume of unlabeled observations. This is a common scenario in web search and natural language processing, where labeling every document is impossible, but collecting raw text is virtually free. By using the labeled data to seed our initial estimations and using unsupervised assumptions, such as the cluster assumption that states that points close to each other should share the same label, we can propagate labels across the unlabeled cloud. This hybrid approach allows us to train high-performance classifiers at a fraction of the traditional labeling cost, combining the strength of both paradigms. To master the art of model selection and construction, we must confront the central paradox of statistical learning, the bias-variance trade-off. Every statistical model we build, from a simple straight line to a massive neural network, is an attempt to capture a complex real-world process using limited data. In this pursuit, we are constantly balanced between two opposing forces of error. If we make our model too simple, it will fail to capture the true underlying patterns. If we make it too complex, it will mistake random noise for reality. The mathematical decomposition of prediction error formalizes this tension, providing us with a clear engineering compass to guide our design decisions and prevent production failures. Let us dissect the mathematics of the bias-variance trade-off using a regression framework. Suppose we have trained a model f-hat using a specific dataset, and we want to evaluate its prediction accuracy at a new, unseen input point, which we call x0. The true response at this point is y0, which is equal to the true function f evaluated at x0 plus our random noise term epsilon. The expected prediction error, or the test mean squared error, at this point can be mathematically decomposed into three distinct components. Specifically, the expected test mean squared error is equal to the squared bias of our estimated function f-hat, plus the variance of our estimated function f-hat, plus the variance of the irreducible error term epsilon. To build a deep understanding of this equation, we must clarify what we mean by the expectation operator, represented by the capital letter E. The expected value represents the average error we would obtain if we were to repeat the entire process of collecting training data, fitting the model, and making a prediction at x0 thousands of times. Each time we collect a new training set, our estimated function f-hat will be slightly different because the training data points themselves fluctuate. Therefore, f-hat evaluated at x0 is not a fixed number. It is a random variable. The true function f evaluated at x0, however, is a fixed, constant value representing the underlying physical reality. Epsilon is also a random variable with a mean of 0 and a constant variance. When we write out the mathematical derivation of the expected prediction error, we begin by looking at the square difference between the true response y0 and our prediction y-hat, which is f-hat evaluated at x0. By expanding this difference and taking the expected value, we find that the terms containing epsilon separate from the terms containing f-hat because epsilon is completely independent of our training data and our input features. The expected value of the cross products between the model's estimation error and the noise term becomes 0 because the average value of epsilon is 0. This mathematical separation leaves us with two distinct parts: the error due to our estimation of f, which is the reducible error, and the variance of epsilon, which is the irreducible error. Let us now examine the reducible error portion, which we decompose further into bias and variance. To do this, we add and subtract the expected value of our model's predictions inside the equation. Through algebraic expansion, we split the estimation error into two squared components. The first component is the difference between the true value of the function f at x0 and the average prediction of our model across all possible training sets. This is the definition of bias. The second component is the expected squared difference between our model's prediction from a single training set and its average prediction across all training sets. This is the definition of variance. Because these two components represent orthogonal statistical properties, their cross-product term also cancels out during expectation, leaving us with the clean sum of squared bias plus variance. Understanding each of these three components individually is key to developing a strong intuitive grasp of model behavior. The first term, bias, measures the error that is introduced by approximating a highly complex real-world phenomenon with a much simpler mathematical model. For example, if the true relationship between marketing spend and sales is a complex S-shaped curve, and we choose to model it as a simple straight line, our linear model will have high bias. No matter how much training data we collect, a straight line can never fit a curve. The bias is the systematic deviation of our average model prediction from the true underlying function. Spatially, if you were to train our model on 1,000 different random datasets and average all their predictions, the bias represents how far that average prediction lies from the true value. The second term, variance, measures the stability of our model's predictions across different datasets. In other words, variance refers to the amount by which our estimated function f hat would change if we had trained it using a completely different training dataset. A model with high variance is highly sensitive to the specific data points used during training. If we change even a few data points, the model's predictions will shift dramatically. Non-parametric models like high-degree polynomials or deep decision trees typically exhibit high variance because they bend and twist to accommodate every individual training point. Spatially, high variance means that our estimated surface wiggles violently, changing its shape completely from one training run to the next. The third term is the variance of the irreducible error, epsilon. As we discussed in our first chapter, this represents the random noise that is fundamentally independent of our input features. Because it is irreducible, it is completely unaffected by our choice of model, the volume of our training data, or the complexity of our architecture. It represents an absolute lower bound on our prediction error, a constant baseline that we can never surpass. To visualize the relationship between bias and variance, imagine a target archery board with a bullseye in the center. The bullseye represents the true value we are trying to predict. Each shot we fire represents a prediction made by a model that has been trained on a different random sample of data. A model with high bias and low variance will shoot a tight cluster of arrows that is located far away from the bullseye. The predictions are consistent, but they are systematically wrong. A model with low bias and high variance, on the other hand, will shoot arrows that are scattered all across the board. The average position of all the arrows might lie exactly in the center of the bullseye, but individual shots are highly erratic and unpredictable. The ideal model, representing low bias and low variance, will place a tight cluster of arrows directly in the center of the bullseye. In practice, as we increase the flexibility or complexity of our model, the bias and variance behave in opposite directions. A simple model, like a linear regression, has high bias because it makes rigid assumptions, but it has low variance because the estimated line is stable and does not change much with new training samples. As we introduce more parameters, allow more nonlinear shapes, or decrease regularization, the bias begins to fall because the model can now capture the true curvature of the function. However, the variance simultaneously begins to rise because the model gains the freedom to adjust to the specific noise present in the training set. If we plot the test mean squared error as a function of model flexibility, we observe a U-shaped curve. Initially, as flexibility increases, the decrease in bias is much larger than the increase in variance, causing the total test error to decline. However, at a certain point, further increases in flexibility yield only minor reductions in bias, while the variance begins to spike. The total test error starts to climb, marking the transition into overfitting. Transitioning from mathematical concepts to engineering design decisions requires us to actively manage this trade-off through architectural choices and hyperparameter tuning. When designing a production system, we do not have access to the true function f, meaning we cannot directly calculate the bias and variance. Instead, we must use empirical methods to locate the bottom of that U-shaped test error curve. This is where cross-validation becomes an essential engineering tool. By partitioning our historical data into multiple training and validation folds, we can simulate the performance of our model on unseen data. The computational cost of cross-validation scales linearly with the number of folds and the complexity of the model. For massive datasets, running a 10-fold cross-validation on a highly flexible model can require significant compute time and memory, forcing engineers to balance the desire for optimal hyperparameter tuning with the practical constraints of training pipelines. To control the variance of highly flexible models without sacrificing their ability to learn complex patterns, engineers use regularization. Regularization is the practice of adding a penalty term to our model's loss function to discourage the parameters from growing too large. In linear models, this is implemented as ridge regression, which penalizes the sum of squared weights, or lasso regression, which penalizes the sum of absolute weights. Mathematically, regularization deliberately introduces a small amount of bias into our model by pulling the parameter estimates towards zero. In exchange for this slight increase in bias, we achieve a massive reduction in variance. The model's predictions become much more stable, preventing the estimated surface from wiggling in response to training noise, and ultimately lowering the overall test error. Let us compare the geometric characteristics of ridge and lasso regularization to understand how they restrict the parameter space. Ridge regularization, or L2 regularization, adds a penalty term equal to the sum of the squared values of the coefficients, multiplied by a hyperparameter lambda. This constraint restricts the parameter values to a multidimensional sphere. The optimization algorithm seeks to minimize the loss while keeping the parameter vector within this sphere. As lambda increases, the sphere shrinks, squeezing all coefficients towards zero, but never setting them exactly to zero. Lasso regularization, or L1 regularization, adds a penalty equal to the sum of the absolute values of the coefficients. This constraint restricts the parameter values to a multidimensional diamond with sharp corners. Because the corners of the diamond lie on the coordinate axis, the optimization contours are highly likely to intersect the constraint boundary at a corner, setting one or more coefficients exactly to zero. This makes lasso an effective tool for automatic feature selection, as it eliminates non-informative features from our model entirely. To push our engineering understanding further, we must examine a modern phenomenon that challenges the classical U-shaped error curve, the concept of double descent. In classical statistical learning theory, we assume that increasing model complexity beyond the interpolation threshold, the point where the model has enough parameters to achieve zero training error, will cause the test error to increase indefinitely due to exploding variance. However, researchers have discovered that if we continue to increase model complexity far beyond the interpolation threshold, entering the overparameterized regime, the test error peaks and then begins to decrease again, forming a second descent. This double descent curve occurs because, in the overparameterized regime, there are infinitely many parameter configurations that can fit the training data perfectly. When we train these massive models using gradient descent with implicit regularization, the optimizer naturally selects the parameter configuration that has the minimum norm. This minimum norm solution represents the smoothest possible function that interpolates the data points, resulting in low variance and excellent generalization on the test set. Understanding double descent allows modern engineers to build and train massive neural networks with billions of parameters, knowing that they can bypass the classical overfitting peak and achieve state-of-the-art performance. Let us examine a production case study where this trade-off is critical: a credit default risk scoring model for a financial institution. The bank wants to predict the probability that a loan applicant will default on their payments. The input features include the applicant's credit history, income-to-debt ratio, employment length, and recent spending behaviors. The response variable is a binary indicator of default. In this scenario, a model with high variance is an operational nightmare. Suppose the engineering team deploys a highly flexible, unregularized decision tree ensemble. This model can capture intricate interactions between features, but its predictions are highly unstable. If the model is retrained on a new month of data, the risk scores for identical applicants might swing wildly. An applicant who was classified as low risk last week might suddenly be flagged as high risk, disrupting the bank's lending operations and frustrating customers. Furthermore, the model may overfit to temporary economic anomalies present in the training window, such as a localized holiday spending spike, mistaking it for a permanent credit risk indicator. To build a reliable system, the team must balance the trade-off. They start with a baseline logistic regression model which has low variance but high bias, as it assumes that all risk factors interact linearly. To capture nonlinear relationships without introducing unacceptable variance, they transition to a regularized gradient boosting machine. They implement L2 regularization and limit the maximum depth of the trees to restrict model flexibility. To find the optimal balance, they run a grid search cross-validation, plotting the training and validation loss curves. They select the hyperparameter configuration that minimizes validation loss, ensuring that the model is flexible enough to capture credit risk signals while remaining stable enough to provide consistent credit scoring over time. Troubleshooting and debugging bias and variance in production requires analyzing learning curves and monitoring performance telemetry. A learning curve plots the model's training error and validation error as a function of the number of training examples. By examining the shape and gap of these curves, you can quickly diagnose whether your system is suffering from high bias or high variance. If your model is suffering from high bias, both the training error and the validation error will be high, and they will lie very close to each other. Spatially, this means the model is underfitting. It is simply not complex enough to represent the data. When you see this pattern, adding more training data will not help. If your model is a straight line, feeding it 1,000,000 points instead of 1,000 will not allow it to curve. To debug high bias, you must increase the complexity of your model. You can do this by adding more features, engineering polynomial terms, or switching to a more flexible algorithm, such as moving from a linear model to a neural network. If your model is suffering from high variance, you will see a massive gap between a very low training error and a significantly higher validation error. This indicates that the model has successfully memorized the training data, including its random noise, but is failing to generalize to the validation set. To debug high variance, you must restrict the model's flexibility. You can achieve this by gathering more training data, which constrains the model by forcing it to find a general solution that fits a wider range of points. Alternatively, you can apply stronger regularization, perform feature selection to remove noisy inputs, or reduce the number of parameters in the model. By implementing automated CI/CD checks that generate learning curves and monitor validation error gaps during retraining cycles, you can prevent overfitting models from leaking into production. To build a deeper appreciation of the mechanics that govern model training, we must investigate the dual hazards of overfitting and underfitting, which represent the practical manifestations of the bias-variance trade-off. Every time we train a machine learning algorithm, we are attempting to solve an optimization problem. We want to find a set of parameters or rules that minimizes our model's error on our training data. However, the true test of a machine learning system is not how well it performs on the data it has already seen, but how well it generalizes to new, unseen observations. When we fail to balance model complexity with the information density of our dataset, our model drifts into either underfitting or overfitting, leading to poor generalization and system instability. Let us begin by defining underfitting from a spatial and conceptual perspective. Underfitting occurs when our model is too simple to capture the underlying structure of the data. This is the spatial equivalent of trying to represent a spherical globe with a flat piece of paper without making any cuts or folds. The model lacks the mathematical capacity or flexibility to represent the true relationship. In a regression setting, if the relationship between the inputs and the outputs is highly nonlinear, and we attempt to fit it using a simple linear regression model, the model will underfit. Spatially, our flat, estimated plane will slice straight through the curved space, missing the peaks and valleys entirely. The model will exhibit high training error and equally high validation error, indicating that it has failed to learn the systematic patterns in the data. Overfitting represents the opposite failure mode. Overfitting occurs when our model is too flexible relative to the amount and noise of our training data. In this scenario, the model has so many parameters or such high mathematical capacity that it does not just learn the underlying systematic relationship. It also learns the random fluctuations, the measurement errors, and the temporary anomalies present in the training set. Spatially, instead of drawing a smooth, generalized curve through the cloud of data points, an overfitted model draws a highly complex, jagged line that twists and bends to touch every single data point. The training error drops to near zero, but the model has essentially memorized the training set. When we feed this model new, unseen data points, its predictions will fail catastrophically because the random noise it memorized does not repeat in the new dataset. To understand why overfitting occurs, we must examine the relationship between the number of observations, which we denote as n, and the number of features, which we represent as p. If the number of features p is close to or greater than the number of observations n, even a simple linear model will overfit the data. This occurs because the model has enough degrees of freedom to find a combination of parameters that fits the training points perfectly, even if there is zero relationship between the features and the target. Furthermore, the rate of overfitting increases as the noise variance of our data increases. When the training data is highly noisy, a flexible model will interpret the random fluctuations as systematic patterns, creating steep artificial peaks and valleys on our estimated surface that do not generalize to the test set. The concept of model complexity is the central dial that engineers turn to control this behavior. Model complexity can be defined mathematically and structurally in several ways depending on the algorithm. In linear models, complexity is determined by the number of independent features we include, which corresponds directly to the degrees of freedom in our statistical estimation. In polynomial regression, complexity is defined by the degree of the polynomial, where higher degrees allow the fitted line to bend more times. In decision trees, complexity is controlled by the depth of the tree, the number of leaf nodes, or the minimum number of samples required to split a node. In deep neural networks, complexity scales with the number of layers, the number of hidden units per layer, and the total count of trainable parameters. To measure model complexity in nonlinear or nonparametric models, statisticians use the concept of effective degrees of freedom. In k-nearest neighbors regression, for example, the complexity is not determined by a count of parameters, because the algorithm has no parameters. Instead, the complexity is determined by the value of k, the number of neighbors we average. When k is equal to 1, the model is highly flexible and wiggles to touch every individual training point, representing high complexity and 1 degree of freedom per training sample. As k increases, the model averages over more points, making the estimated surface smoother and less flexible, which represents a reduction in the effective degrees of freedom and a decrease in model complexity. As we increase model complexity, the training error behaves in a highly predictable manner. Because a more complex model has more mathematical freedom to fit the training data, the training error will monotonically decrease as complexity increases. If we give a polynomial model enough degrees of freedom, it can fit a dataset of 50 points with 0 training error. However, the test error, which represents generalization performance, follows a U-shaped trajectory. At low levels of complexity, the model underfits, resulting in high test error. As we increase complexity, the test error decreases as the model begins to capture the systematic signal. This brings us to the optimal point of generalization, where the test error reaches its absolute minimum. If we continue to increase complexity beyond this point, the test error begins to climb as the model transitions into overfitting, memorizing the training noise and diverging from the validation set. The gap between the training error and the validation error widens progressively, acting as a clear mathematical signature of overfitting. Transitioning this understanding into engineering design decisions requires us to select strategies that actively constrain model complexity. One of the most effective approaches is feature selection, which involves systematically removing redundant or noisy inputs from our feature space. By reducing the number of input features, we decrease the model's degrees of freedom, effectively lowering its complexity and reducing the risk of overfitting. Alternatively, we can use dimensionality reduction techniques like principal component analysis to project our features into a lower dimensional space, capturing the maximum variance with fewer variables. Another critical engineering design decision is early stopping, which is widely used when training iterative algorithms like gradient-boosted trees or neural networks. During the training process, the algorithm updates its parameters step by step to minimize training loss. By monitoring the validation loss at each step, we can stop the training process the moment the validation loss stops improving and begins to rise. This prevents the model from continuing to optimize on the training set once it has finished learning the systematic signals. To locate the optimal model complexity, we must design robust validation schemes, which introduces a choice between different cross-validation strategies. The simplest approach is the validation set method, where we set aside a single random portion of our data for testing. While computationally cheap, this method is highly sensitive to the specific random split, and the validation error estimate can be highly variable. To obtain more stable estimates, we use k-fold cross-validation. We partition our data into k-equal folds, train the model k times using k-1 folds, and validate it on the remaining fold, averaging the evaluation metrics across all runs. If we set k equal to the number of observations n, we obtain leave one out cross-validation, which we refer to as LOCV. LOCV has the advantage of being virtually unbiased because the training sets contain almost all data points. However, LOOKV is computationally expensive and exhibits high variance because the n different models are trained on almost identical datasets, making their predictions highly correlated and causing their average to have higher variance than a standard 10-fold cross-validation. To ground these concepts in a production environment, let us study a case study of a click-through rate prediction engine for a digital advertising platform. The platform's goal is to predict the probability that a specific user will click on an advertisement displayed on a website. The features include the user's demographic history, their recent search queries, the category of the website, and the specific attributes of the ad. The response variable is a binary click or no-click indicator. In this high-scale environment, underfitting and overfitting have direct financial consequences. If the prediction engine is too simple, for instance, if the team deploys a basic logistic regression model that only looks at a few broad features, the model will underfit. It will predict a uniform click probability for wide segments of users, failing to capture subtle interactions like the fact that sports enthusiasts are more likely to click on fitness ads in the morning than in the evening. As a result, the platform will display irrelevant ads, leading to a drop in user engagement and lost advertising revenue. Conversely, if the team uses a highly complex model without constraints, such as a deep neural network that trains on sparse, high cardinality features like individual ad IDs and user IDs, the model will overfit. It will memorize specific, rare occurrences. If a single user accidentally clicks on a specific ad once, the model might assign a click probability of near 1 to that specific combination, ignoring all general patterns. When the platform serves ads based on these overfitted predictions, the actual click rates will collapse because the rare co-occurrences do not represent general user behavior. To resolve this, the engineering team designs a regularized logistic regression model using L1 regularization, which performs automatic feature selection by driving the weights of non-informative features to 0. They run k-fold cross-validation on historical log data, evaluating the model's performance using area under the receiver operating characteristic curve. By tuning the regularization strength, they constrain the model's complexity, ensuring it generalizes well to new users and novel ads, maximizing ad relevance and platform revenue. Troubleshooting and debugging overfitting and underfitting in a production pipeline requires a systematic approach to identifying where the training process has gone wrong. When a model exhibits poor performance, the first step is to analyze the relationship between the training loss and the validation loss. If your model is underfitting, the diagnostic signature is a training loss that is unacceptably high, paired with a validation loss that is nearly identical to the training loss. To debug this, you must increase the capacity of the model. You can begin by engineering interaction features, combining individual variables, such as multiplying user age by income, to capture nonlinear relationships. You can also reduce the strength of your regularization parameters, allowing the model weights more freedom to adjust to the training signal. If these steps are insufficient, you must transition to a more flexible model architecture, such as moving from a linear model to a nonlinear tree-based ensemble. If your model is overfitting, the signature is a training loss that is extremely low, but a validation loss that is high and increasing. To debug overfitting, you must apply constraints. You can start by increasing the volume of your training data, which increases the signal-to-noise ratio and makes it harder for the model to memorize individual points. You can also apply L2 regularization to penalize large weights, or implement dropout in neural networks to randomly deactivate units during training, forcing the network to learn redundant representations. Another critical debugging step is to check for data mismatch. Data mismatch occurs when the distribution of the data used for validation is different from the distribution used for training. For example, if you train a speech recognition model on clean studio audio and validate it on noisy street recordings, the model's validation performance will fail. This is not a failure of model complexity, but a distribution shift. By collecting representative data and aligning your training and validation distributions, you can isolate complexity issues from environmental mismatches, ensuring your models remain robust in production. To build robust validation frameworks, we must also address the challenges of time series data, where the standard assumption of independent and identically distributed observations is violated. If we use standard random k-fold cross-validation on time series data, we will leak future information into the past. For example, if we predict tomorrow's stock price using yesterday's and today's data, and our training set includes data from next week, our model will learn look-ahead patterns that cannot exist in production. To prevent this look-ahead bias, engineers use temporal splits, such as rolling window validation or time series split. In this approach, the training fold only contains observations that occurred before the validation fold, simulating the actual temporal flow of production predictions and ensuring that our evaluations reflect true generalization. We must also evaluate how feature engineering acts as a primary driver of model complexity. Feature engineering is the process of using domain knowledge to create new features from raw inputs, such as extracting the day of the week from a timestamp or calculating the ratio between two variables. While feature engineering can significantly improve a model's performance by presenting the systematic signals in a more digestible format, it also increases the dimensionality of our feature space. If we expand our features indiscriminately, for instance by performing polynomial expansions that multiply every feature by every other feature, we can quickly exceed our sample size limits, shifting our model from underfitting to overfitting. Therefore, engineers must pair feature engineering with strict feature selection and regularization pipelines, balancing the search for new predictive signals with the necessity of keeping the feature space compact. To implement these validation and regularization steps efficiently, engineers use model registry systems to track experiments. During hyperparameter tuning, we generate hundreds of model candidates, each with different training runs and validation metrics. Storing these metrics in spreadsheets or logs is a recipe for operational chaos. By using systems like MLflow or weights and biases, we can log every training run, saving the exact hyperparameters, validation curves, feature importance scores, and model artifacts. This centralized tracking allows us to compare different architectures objectively, select the optimal configuration, and ensure that our production deployments are backed by reproducible scientific data. To automate the search for the optimal feature subset during exploratory analysis, engineers use subset selection methods. In best subset selection, we evaluate all possible combinations of our features, which is computationally expensive because the number of combinations scales exponentially with the number of features. For a dataset with 20 features, we must train over 1 million models. To reduce this computational burden, we use stepwise selection methods, such as forward stepwise selection or backward stepwise selection. In forward stepwise selection, we start with a model containing no features and sequentially add the single feature that improves performance the most, continuing until no further improvement is observed. In backward stepwise selection, we start with the full model containing all features and sequentially remove the least useful variables. These stepwise heuristics reduce our compute costs from exponential to quadratic, allowing us to find highly predictive, low-complexity models in a fraction of the time. To establish a mathematical language capable of processing thousands of variables simultaneously, we must ground our understanding in linear algebra. In traditional algebra, we deal with single numbers, which we call scalars. However, in machine learning, a single data point is rarely a single number. It is a collection of features, such as a user's age, income, and browsing history. To represent and manipulate these collections efficiently, we group them into vectors and matrices. Linear algebra is not merely a set of rules for multiplying arrays of numbers. It is the study of geometric transformations in high-dimensional spaces. By mastering the spatial intuitions of vectors, matrices, dot products, and eigenvalues, you can understand how models manipulate space to uncover hidden structures. Let us start with the vector, the fundamental building block of linear algebra. Spatially, a vector can be visualized as an arrow starting at the origin of a coordinate system and pointing to a specific location in space. The dimensions of the space correspond to the number of features in our dataset. If we have a dataset with 3 features, each data point is a vector pointing to a coordinate in a 3-dimensional room. The length of the arrow represents the magnitude of the vector, and the direction in which it points represents the ratio between the features. In machine learning, we treat every observation as a vector, allowing us to use geometric concepts like distance and angle to compare different data points. To measure the length or size of these vectors, we use the mathematical concept of a vector norm. The 2 most common norms are the L1 norm and the L2 norm. The L2 norm, or Euclidean norm, is calculated by squaring each element of the vector, summing them, and taking the square root. Spatially, this corresponds to the straight-line distance from the origin to the point represented by the vector. The L1 norm, or Manhattan norm, is calculated by summing the absolute values of the elements. Spatially, this corresponds to the distance you would travel if you were restricted to walking along grid lines like city streets. In regularization, the geometry of these norms plays a critical role. The L2 norm restricts parameters to a smooth sphere, while the L1 norm restricts them to a diamond with sharp corners, influencing how models scale and select features. The dot product is the primary operation we use to compare 2 vectors. Mathematically, the dot product is calculated by multiplying the corresponding elements of 2 vectors and summing the results. Spatially, the dot product measures the extent to which 2 vectors point in the same direction. If you project one vector onto another and multiply the length of that projection by the length of the second vector, you obtain the dot product. If 2 vectors are perpendicular, meaning they point in completely independent directions, their dot product is 0. If they point in the exact same direction, their dot product is positive and maximized. If they point in opposite directions, it is negative. In engineering, we use the dot product as a fundamental measure of similarity, and it forms the mathematical core of cosine similarity and linear projection. A matrix is a collection of vectors organized into rows and columns. While you can think of a matrix as a 2-dimensional spreadsheet, its spatial representation is much more dynamic. A matrix represents a linear transformation. When you multiply a vector by a matrix, the matrix transforms the vector, moving it to a new location in space. This transformation can stretch, rotate, reflect, or shear the space. Matrix multiplication is simply the composition of multiple transformations. If you multiply a vector by matrix A and then by matrix B, it is equivalent to applying both transformations in sequence. The system of linear equations represented by the equation a times x equals b is a quest to find the vector x that, when transformed by matrix A, lands precisely on the target vector b. To understand whether a system of equations has a unique solution, we must explore the concepts of linear independence, span, and matrix rank. A set of vectors is linearly independent if no vector in the set can be written as a combination of the others. The span of a set of vectors is the entire multidimensional space that can be reached by scaling and adding those vectors together. The rank of a matrix is the maximum number of linearly independent columns or rows it contains, representing the actual dimensionality of the space after the transformation is applied. If a matrix has full rank, it preserves the dimensions of the space. If it is rank deficient, it collapses one or more dimensions, projecting a three-dimensional space onto a flat plane or a straight line, which represents a permanent loss of information. Symmetric matrices represent a special class of transformations that are widely encountered in machine learning, particularly in covariance analysis. A matrix is symmetric if it is equal to its transpose, meaning the element at row I column j is identical to the element at row j column I. Symmetric matrices have a remarkable geometric property described by the spectral theorem. They can always be diagonalized using an orthogonal matrix of their eigenvectors. This means that for any symmetric matrix, the eigenvectors are completely perpendicular to one another, and they form a new orthogonal coordinate system that aligns perfectly with the principal axis of the transformation. Eigenvalues and eigenvectors represent the invariant properties of these linear transformations. When a matrix transforms a space, it typically rotates and stretches almost every vector within that space. However, there are always special, privileged directions that do not change their orientation during the transformation. The vectors that lie along these directions are called eigenvectors. When you multiply an eigenvector by the matrix, the resulting vector points in the exact same direction, only scaled in length. The factor by which the eigenvector is scaled is called the eigenvalue. Spatially, eigenvectors represent the axis of symmetry of the transformation, the directions along which the space is stretched or compressed without rotation. To generalize these concepts to non-square matrices, engineers use singular value decomposition, which we refer to as SVD. While eigenvectors and eigenvalues only exist for square matrices, SVD decomposes any arbitrary matrix of size m by n into three constituent matrices: an orthogonal matrix of left singular vectors, a diagonal matrix of singular values, and another orthogonal matrix of right singular vectors. Spatially, SVD breaks down any complex transformation into three sequential steps: a rotation in the input space, a scaling along the coordinate axis by the singular values, and a final rotation in the output space. SVD is a powerful tool for matrix factorization, latent semantic analysis, and dimensionality reduction. Transitioning to engineering design decisions, the way we represent and compute these matrix operations determines the scalability of our machine learning pipelines. In production, we frequently encounter two types of matrices: dense matrices, where most elements are non-zero, and sparse matrices, where the vast majority of elements are zero. Storing a sparse matrix as a dense two-dimensional array is an engineering failure, as it wastes massive amounts of memory storing zeros. Instead, we use specialized sparse formats, such as compressed sparse row or coordinate formats, which only store the indices and values of non-zero elements. This reduces the memory footprint of our data pipelines from gigabytes to megabytes, allowing us to load massive user item interaction matrices directly into memory. The computational cost of matrix operations also dictates our choice of hardware. Multiplying two dense matrices of size n by n has a naive time complexity of O of n cubed. While advanced algorithms can reduce this slightly, matrix operations remain computationally intense. To handle this load, modern engineering pipelines offload matrix computations from CPUs to GPUs. A CPU is designed for sequential processing, featuring a few highly complex cores. A GPU, conversely, contains thousands of simple, parallel cores designed to execute the same instruction on multiple data streams simultaneously. This single instruction multiple data, or SIMD, architecture is perfectly suited for matrix multiplication, which consists of millions of independent dot products. However, using GPUs introduces an engineering trade-off: the data transfer bottleneck. Before the GPU can perform a computation, the data must be copied from host CPU memory to GPU device memory across the PCIe bus. If your matrix operations are small, the latency of this data transfer will exceed the computational savings, resulting in slower execution times than on the CPU. Therefore, engineers must batch their data and perform large, vectorized computations to justify the cost of GPU acceleration. To understand how these concepts are applied in practice, let us examine a production case study involving PCA for image compression in a facial recognition system. A security application captures high-resolution images of faces, where each image contains thousands of pixels. If we treat each pixel as a feature, each face is a vector in a space with thousands of dimensions. Running classification algorithms directly in this high-dimensional space is computationally prohibitive and prone to overfitting. To compress these images without losing the critical features that distinguish one face from another, the engineering team uses PCA. PCA relies on calculating the covariance matrix of the dataset, which measures how the brightness of each pixel varies in relation to every other pixel. The team then calculates the eigenvectors and eigenvalues of this covariance matrix. Spatially, the eigenvector with the largest eigenvalue points in the direction of the greatest variance in the dataset. This direction represents the most significant pattern of variation among the faces, which we call a principal component. By selecting the top 50 eigenvectors, those associated with the largest eigenvalues, the team constructs a projection matrix. They project the high-dimensional facial vectors onto this lower-dimensional space, transforming each face from a 1,000-pixel vector into a compact vector of 50 principal component scores. This compression reduces storage requirements, accelerates inference speed, and filters out high-frequency sensor noise, allowing the downstream classification models to run with minimal latency and high accuracy. Debugging linear algebra operations in production requires vigilance against numerical instability, which frequently manifests as singular or ill-conditioned matrices. A matrix is singular if its determinant is zero, meaning it collapses one or more dimensions of the space, making it impossible to invert. An ill-conditioned matrix is one that is close to singular, where its condition number, the ratio of its largest singular value to its smallest singular value, is extremely high. In linear regression, estimating the parameters requires inverting the matrix product X transpose X. If your input features are highly correlated, a condition known as multicollinearity, the matrix X transpose X becomes ill-conditioned. When you attempt to invert it using standard floating point arithmetic, the round-off errors multiply exponentially. The resulting parameter estimates will swing wildly, exhibiting massive values that are highly sensitive to minor variations in the training data. This numerical instability can cause gradient descent algorithms to diverge, leading to exploding gradients that crash the training pipeline. To debug and prevent these numerical failures, engineers use SVD to analyze the singular value spectrum of their data matrices. If the condition number is too high, the standard solution is to apply ridge regularization. By adding a small positive scalar multiplied by the identity matrix to X transpose X before inversion, we mathematically guarantee that the matrix is invertible and well-conditioned. This operation shifts all eigenvalues away from zero, stabilizing the inverse calculation and protecting the training pipeline from floating-point overflow. By monitoring matrix condition numbers and eigenvalue distributions in your data validation pipelines, you can catch numerical instability before it disrupts your production training loops. To deepen our understanding of matrix transformations, we must look at how matrix multiplication behaves under algebraic operations. Unlike scalar multiplication, matrix multiplication is non-commutative. This means that if we have two matrices A and B, the product A times B is not equal to the product B times A. Spatially, this is intuitive. Rotating a space by 90 degrees and then shearing it is not the same as shearing the space first and then rotating it. However, matrix multiplication does satisfy the associative and distributive properties, allowing us to group and distribute transformations in complex equations. This non-commutative nature requires engineers to be extremely careful with the order of operations in their code, as swapping the order of matrix products will result in dimension mismatches or incorrect calculations. We must also explore the geometric meaning of the matrix determinant. The determinant is a scalar value calculated from a square matrix that represents the scaling factor of volume under the transformation. Spatially, if you take a unit square in two-dimensional space and apply the transformation represented by matrix A, the area of the resulting shape will be equal to the determinant of A. If the determinant is negative, it indicates that the transformation has flipped the orientation of the space, like reflecting it in a mirror. If the determinant is exactly zero, it means the transformation has collapsed the space, reducing its dimensionality and compressing all volumes to zero. This zero-volume compression is why a matrix with a determinant of zero is singular and cannot be inverted. You cannot uncollapse a flat plane back into a three-dimensional room because the information in the collapsed dimension has been lost. To utilize these concepts for collaborative filtering in recommendation systems, engineers use singular value decomposition. In a user movie rating matrix, rows represent users and columns represent movies, with the cells containing ratings. Because users only watch a tiny fraction of all movies, this matrix is sparse and incomplete. By applying SVD, we decompose this rating matrix into latent user profiles and latent movie profiles. Spatially, we project both users and movies into a shared low-dimensional latent space. If a user's latent vector points in the same direction as a movie's latent vector, their dot product will be positive and high, indicating a strong recommendation score. This low-rank matrix approximation allows us to predict missing ratings and recommend movies to users based on their alignment in the latent space. We must also understand the deep mathematical connection between a matrix's eigenvalues and its basic trace and determinant properties. The trace of a square matrix is defined as the sum of its diagonal elements. A fundamental theorem of linear algebra states that the trace of a matrix is exactly equal to the sum of its eigenvalues. Similarly, the determinant of a matrix is exactly equal to the product of its eigenvalues. This relationship means that if even a single eigenvalue of a matrix is 0, the product of its eigenvalues will be 0, resulting in a determinant of 0. This zero-determinant matrix is singular and cannot be inverted. This connection explains why rank-efficient covariance matrices, which contain collinear features, have zero-value eigenvalues that cause matrix inversion algorithms to fail during linear regression training, illustrating the unity between eigenvalues, determinants, and numerical stability. To compare vectors in high-dimensional spaces, we must choose between Euclidean distance and cosine similarity based on our data characteristics. Euclidean distance, which is the L2 norm of the difference vector, measures the absolute distance between 2 points, making it highly sensitive to the magnitude of the features. Cosine similarity, which is the dot product of two vectors divided by the product of their L2 norms, measures the cosine of the angle between them, representing their directional alignment while completely ignoring their magnitude. For example, in text recommendation, if one user reads 10 articles about sports and another user reads 100 articles about sports, their raw coordinate vectors will have different lengths. Using Euclidean distance would suggest they are highly dissimilar, whereas cosine similarity would recognize their identical alignment, making it the preferred metric for text embeddings and high-dimensional sparse representations. To navigate the uncertainty inherent in real-world observations, we must turn to the mathematics of probability and statistics. In our study of statistical learning, we defined the error term epsilon as a random variable representing the noise we cannot predict. However, to work with randomness in an engineering environment, we cannot treat it as an unknowable mystery. We must quantify it. Probability theory provides us with the mathematical tools to define, model, and manipulate random processes. By understanding probability distributions and mastering the predictive mechanics of Bayes' theorem, we can build systems that make rational decisions under uncertainty, updating their beliefs as new data arrives. Let us begin by establishing the formal definition of a probability space, which consists of 3 components: a sample space, a collection of events, and a probability measure. The sample space is the set of all possible outcomes of a random experiment. An event is a specific subset of these outcomes, such as rolling an even number on a die. The probability measure is a function that assigns a number between 0 and 1 to each event, satisfying the fundamental Kolmogorov axioms of probability. These axioms dictate that the probability of any event must be non-negative, the probability of the entire sample space must be exactly 1, and the probability of the union of mutually exclusive events must be the sum of their individual probabilities. A random variable is a mathematical function that maps the outcomes of a random process to real numbers, allowing us to apply algebraic operations to uncertainty. We classify random variables into 2 types: discrete, which take on a countable set of distinct values, and continuous, which can take on any value within an interval. To describe the behavior of these variables, we use probability distributions. For discrete variables, we use a probability mass function, which gives the exact probability for each possible value. For continuous variables, we use a probability density function, which we refer to as a PDF. Spatially, for a continuous random variable, the probability of obtaining any single exact value is 0, as there are infinitely many points. Instead, we represent the probability distribution as a smooth curve, where the probability that the variable falls within an interval is represented by the area under the PDF curve bounded by that interval. The cumulative distribution function, or CDF, represents the accumulated probability from negative infinity up to a specific value, displaying a curve that rises smoothly from 0 to 1. Several key distributions serve as the primary components of our machine learning models. The Gaussian or normal distribution is the classic bell-shaped curve characterized by its mean and variance, which describes phenomena that cluster around a central value, such as measurement errors. Spatially, the normal distribution exhibits the empirical rule, which states that approximately 68% of the data lies within one standard deviation of the mean, 95% lies within two standard deviations, and 99.7% lies within three standard deviations. The Bernoulli distribution models a single trial with a binary outcome, such as a coin flip or a user clicking an ad. The binomial distribution extends this to model the number of successes in multiple independent trials. The Poisson distribution models the rate of occurrences of rare events over a fixed interval of time or space, such as server requests. The uniform distribution represents a scenario where all outcomes within a range are equally likely, displaying a flat density curve. Bayes' theorem provides the fundamental formula for updating probabilities in the face of new evidence. The theorem states that the posterior probability of an event A given event B is equal to the likelihood of event B given event A, multiplied by the prior probability of event A, divided by the total evidence probability of event B. Spatially, you can visualize Bayes' theorem by imagining a square target representing a sample space of all possible outcomes with an area equal to 1. Suppose we have a circular region representing event A and another overlapping circular region representing event B. The prior probability of A is simply the area of circle A. When we observe that event B has occurred, the sample space collapses. We discard everything outside circle B. The posterior probability of A given B is the fraction of circle B that is occupied by the overlap of A and B. To see the predictive power of Bayes' theorem, let us walk through a classic numerical example involving a medical test. Suppose a rare disease affects 1% of the population, which represents our prior probability. A diagnostic test has a sensitivity of 95%, meaning that if a patient has the disease, the probability of a positive test is 95%. The test also has a false positive rate of 5%, meaning that if a patient does not have the disease, the probability of a positive test is 5%. If a randomly selected patient tests positive, what is the probability that they actually have the disease? Naively, many people assume the probability is 95%. However, applying Bayes' theorem reveals a different reality. The total evidence of a positive test is the sum of true positives and false positives, which is equal to 1% multiplied by 95% plus 99% multiplied by 5%, totaling approximately 5.9%. The posterior probability of having the disease given a positive test is the true positive rate divided by this total evidence, which yields approximately 16%. This surprisingly low probability occurs because the disease is extremely rare, meaning the number of false positives in the healthy population far exceeds the number of true positives, illustrating how Bayes' theorem prevents us from making incorrect inferences by incorporating the prior base rate. Understanding this formula allows us to build generative classifiers, presenting a major engineering design decision when compared to discriminative models. A discriminative model, like logistic regression, models the conditional probability of the target given the features directly. It draws a boundary line between the classes. A generative model, like naive Bayes or linear discriminant analysis, which we refer to as LDA, models the joint probability distribution of the features and the target. It uses Bayes' theorem to calculate the probability of the target by learning what each class looks like. Let us compare LDA and quadratic discriminant analysis, which we call QDA, to understand their geometric trade-offs. Both are generative models that assume the features within each class follow a multidimensional Gaussian distribution. LDA assumes that all classes share the same covariance matrix, which means the Gaussian distributions have the same shape and orientation. This shared covariance assumption simplifies the log ratio of the class probabilities, resulting in a linear decision boundary. QDA, on the other hand, allows each class to have its own distinct covariance matrix, allowing the Gaussian shapes to bend and orient independently. This flexibility results in a quadratic, curved decision boundary. The trade-off is parameter estimation. While LDA only needs to estimate a single shared covariance matrix, QDA must estimate a separate covariance matrix for each class, which scales quadratically with the number of features, leading to high variance and a risk of overfitting on small datasets. When implementing these probability models on computers, engineers must manage numerical precision limits. In naive Bayes, we calculate the joint likelihood of a set of features by multiplying their individual probabilities. Since probabilities are numbers between 0 and 1, multiplying dozens of them together yields an extremely small number. This number will quickly exceed the precision limit of standard 64-bit floating-point variables, resulting under the hood in a numerical underflow where the value is rounded to absolute 0. To resolve this floating-point underflow, engineers perform all probability computations in log space. Instead of multiplying probabilities, we take the natural logarithm of each probability and sum them together. This transformation maps probabilities from the 0 to 1 range to a negative range from 0 to negative infinity. Summing negative numbers is numerically stable and preserves the relative rankings of the probabilities, allowing us to compute classifications without losing precision. To see these concepts applied in production, let us study the case study of a document classification system designed to filter spam email. The input is a raw email text, and the target is a binary label indicating whether the email is spam or ham. The feature vector X represents the presence or absence of specific words in the email vocabulary. For this application, the engineering team chooses a multinomial naive Bayes classifier. The model is called naive because it makes the simplifying assumption that the occurrence of any word in the email is independent of the occurrence of any other word, given the classification of the email. Spatially, this is equivalent to assuming that our high-dimensional probability density shape is aligned perfectly with the coordinate axis with no diagonal stretching. Under this naive assumption, the likelihood of seeing a specific combination of words in a spam email is calculated by multiplying the individual probabilities of each word appearing in spam. During training, the system estimates the prior probability of spam by calculating the ratio of spam emails in the training set. It also estimates the likelihood for each word by counting how often it appears in spam versus ham emails. When a new email arrives, the classifier extracts the words, converts their likelihoods into log probabilities, sums them with the log prior of spam, and compares the result to the log ham calculation. The compute cost is incredibly low, consisting of simple dictionary lookups and additions, which allows the email client to classify thousands of messages per second on the edge device with zero network latency. However, deploying this system reveals a critical debugging challenge known as the zero probability problem. If the training dataset did not contain any spam emails containing the word portfolio, the estimated likelihood of the word portfolio given spam will be calculated as 0. When a new spam email containing the word portfolio arrives, multiplying by 0 will cause the entire spam joint probability to collapse to 0, regardless of all other spam indicators. To debug this failure mode, engineers implement Laplace smoothing, also known as additive smoothing. Laplace smoothing adds a small positive integer, typically 1, to the numerator of the word frequency calculations and adds the vocabulary size to the denominator. This mathematical adjustment ensures that every feature has a non-zero probability, preventing the joint likelihood from collapsing. Another production issue is prior shift. If the proportion of spam in the incoming mail stream spikes due to a coordinated attack, the historical prior probability of spam stored in the model will be too low, leading to high false negative rates. To debug prior shift, the engineering team sets up a monitoring pipeline that tracks the distribution of predicted probabilities. By calculating Brier scores and calibration curves, they measure the alignment between the model's confidence and the actual click rates. If the calibration drifts, they dynamically update the prior term in the Bayesian equation using a sliding window of recent observations, restoring the filter's accuracy without requiring a full retraining of the word likelihoods. To understand how we estimate the parameters of our probability distributions from data, we must compare maximum likelihood estimation, which we call MLE, with maximum a posteriori estimation, which we call MAP. MLE is a frequentist approach that estimates the parameters by finding the values that maximize the likelihood of the observed data. In other words, MLE asks, under which parameter values was our training dataset most likely to occur? Spatially, if we assume our data follows a Gaussian distribution, MLE calculates the sample mean and sample variance, placing the peak of the bell curve directly over the average of the data points. MAP estimation represents a Bayesian extension of this process. Instead of looking only at the likelihood of the data, MAP incorporates a prior probability distribution over the parameters themselves. This prior distribution represents our beliefs or constraints before we observe any training data. Spatially, if we have a prior belief that our parameters should be close to 0, the MAP estimation will pull the estimated parameters towards 0, balancing the likelihood of the data with the prior constraint. Mathematically, this prior distribution acts as the exact equivalent of regularization in supervised learning. A Gaussian prior over the parameters yields L2 regularization, while a Laplacian prior yields L1 regularization. This bridge between Bayesian probability and regularization highlights the unity of statistical learning, showing that what frequentist engineers call regularization is mathematically identical to what Bayesian statisticians call prior beliefs. We must also explore continuous joint probability distributions, which model the relationship between multiple continuous variables. Just as a single continuous variable is described by a PDF, two continuous variables are described by a joint PDF, which represents a three-dimensional surface where the volume under the surface is equal to 1. The marginal probability distribution is the distribution of a single variable, calculated by integrating the joint PDF over all possible values of the other variable. Spatially, this is equivalent to projecting the three-dimensional surface onto one of the coordinate planes, collapsing the other dimension. The conditional probability distribution describes the behavior of one variable given the value of another, which corresponds to taking a slice of the joint PDF surface at a specific coordinate and normalizing its area to 1. To apply the central limit theorem safely, we must verify its underlying mathematical assumptions, specifically the requirement of finite variance. The central limit theorem guarantees that the distribution of sample means will converge to a normal distribution, but this holds true only if the underlying population distribution has a finite mean and a finite variance. If we deal with heavy-tailed distributions that violate this assumption, such as the Cauchy distribution, which has infinite variance and no defined mean, the central limit theorem fails. For Cauchy distributed data, the average of multiple samples does not converge to a single value. Instead, the sample mean fluctuates wildly regardless of how many observations we collect. This failure of convergence is a critical concern in financial engineering, where stock returns and market risks often exhibit heavy-tailed behaviors, forcing modelers to use alternative statistical tools to avoid underestimating the probability of extreme market crashes. Let us write out the mathematical formula for Laplace smoothing to understand how it scales with vocabulary size. The smooth probability of a feature xi given class y is calculated as the frequency of xi in class y plus a smoothing parameter alpha, divided by the total count of all features in class y plus alpha multiplied by the size of the vocabulary, which we represent as the cardinality of v. The parameter alpha, typically set to 1, acts as a pseudo-count, adding a small baseline probability to every word. The term alpha multiplied by the vocabulary size in the denominator ensures that the probabilities of all words in our vocabulary still sum to exactly 1. By adjusting alpha, we control the strength of our prior assumption. A larger alpha pulls the probabilities closer to a uniform distribution, smoothing out the noise of small training sets, while a smaller alpha allows the model to align more closely with the observed frequencies. To begin any successful machine learning project, we must first learn to listen to the data. Before we can fit complex surfaces, optimize parameters, or deploy neural networks, we must understand the shape, distribution, and structural characteristics of the raw variables we have collected. This process is divided into descriptive statistics, which uses numerical summaries to describe the features, and exploratory data analysis, which uses visual and spatial reasoning to uncover relationships, anomalies, and patterns. A common mistake is to treat this phase as a minor mechanical step. In reality, exploratory data analysis is where we build our mental model of the dataset, identify data quality issues, and make the fundamental decisions that determine the success of our downstream models. Let us start by examining the measures of central tendency, which seek to identify the center point of a distribution of values. The most common measure is the mean or average, which is calculated by summing all the observations and dividing by the total count. Spatially, you can visualize the mean as the center of gravity of a physical balance beam, where each data point is a weight placed at its corresponding value. While the mean is mathematically convenient, it is highly sensitive to extreme values or outliers. If we have 9 people who earn $30,000 a year and 1 person who earns $1 million, the mean salary of this group will be $127,000. This average is highly misleading because it does not represent any individual in the group. To handle skewed distributions, we use the median. The median is the physical middle value when all observations are sorted in ascending order. If we have an even number of observations, it is the average of the 2 middle values. Spatially, the median simply splits the distribution in half, with 50% of the points lying below it and 50% lying above it. In our salary example, the median salary is $30,000, providing a much more realistic picture of the group's income. The mode is the value that occurs most frequently in the dataset, representing the tallest peak in a discrete distribution. To fully describe a variable, we must complement measures of central tendency with measures of dispersion, which quantify how spread out the values are from the center. The range is the simplest measure, representing the difference between the maximum and minimum values, but it is entirely dominated by extreme outliers. A more robust measure is the interquartile range, which we refer to as the IQR. To calculate the IQR, we sort our dataset and divide it into 4 equal quarters or quartiles. The first quartile represents the 25th percentile, the second quartile is the median or 50th percentile, and the third quartile represents the 75th percentile. The IQR is the difference between the third quartile and the first quartile, capturing the spatial width of the middle 50% of our data points. In a box plot representation, this middle 50% is drawn as a box, and whiskers extend from the box to the lowest and highest values that lie within 1.5 times the IQR of the quartiles, while any values beyond these whiskers are plotted individually as outliers. To measure the symmetry and tail behavior of our distributions, we use skewness and kurtosis. Skewness measures the asymmetry of the probability distribution around its mean. A distribution is symmetric if it looks the same to the left and right of the center point. If the tail on the right side of the distribution is longer or fatter than the left side, the distribution has positive or right skewness, which is common in wealth and income data. If the tail on the left is longer, it has negative or left skewness. Kurtosis measures the heaviness of the tails of the distribution compared to a normal distribution. A distribution with high kurtosis, which we call leptokurtic, has heavy tails, meaning it exhibits a higher frequency of extreme outliers than a normal distribution. Spatially, heavy tails are highly dangerous for linear models because a single extreme outlier in a heavy-tailed distribution can exert massive leverage on the estimated surface, tilting the entire model away from the general population pattern. The most mathematically common measures of dispersion are variance and standard deviation. Variance is calculated by subtracting the mean from each data point, squaring the result, summing these squared differences, and dividing by the number of observations. Squaring the differences ensures that deviations above the mean do not cancel out deviations below the mean, and it places a heavier penalty on larger deviations. Spatially, variance represents the average squared distance of the points from the center of gravity. Because variance is expressed in squared units, such as squared dollars or squared meters, we take its square root to calculate the standard deviation. The standard deviation is expressed in the same units as the original data, representing the typical distance a data point lies from the mean. Exploratory data analysis extends these summaries by examining the relationships between multiple variables using covariance and correlation. Covariance measures whether two variables move together. If one variable increases when the other increases, their covariance is positive. If one decreases as the other increases, it is negative. However, covariance is scale-dependent, meaning its value changes depending on the units of measurement. To create a dimensionless scale, we divide the covariance by the product of the standard deviations of the two variables, yielding the Pearson correlation coefficient. The Pearson correlation coefficient ranges from -1 to +1, where +1 represents a perfect positive linear relationship, -1 represents a perfect negative linear relationship, and 0 represents no linear relationship. Spatially, Pearson correlation measures how tightly our data points cluster around a straight line. If the relationship is monotonic but nonlinear, for example, if one variable increases exponentially with another, Pearson correlation will underestimate the strength of the association. In such cases, we use the Spearman rank correlation coefficient, which calculates the Pearson correlation on the ranks of the values rather than the raw values themselves, measuring whether the variables move in the same direction regardless of linearity. Transitioning to engineering design decisions, Performing these statistical calculations on large-scale production databases introduces severe memory and compute constraints. In a textbook setting, calculating the variance of a dataset requires 2 passes over the data. First, you loop through all points to calculate the mean, and then you loop through them again to calculate the sum of squared differences. In a production pipeline processing billions of records stored across distributed storage systems, reading the data twice is an engineering anti-pattern. The network and disk input-output costs of loading the dataset twice will throttle performance. To calculate these metrics in a single pass, engineers use Welford's algorithm for computing running mean and variance. Welford's algorithm processes data points one by one, updating the running mean and a running sum of squares incrementally at each step. This approach is mathematically stable and protects against floating-point round-off errors that occur when subtracting large numbers in naive single-pass algorithms. By implementing Welford's algorithm, we can compute the exact mean and variance of a streaming data source using constant memory, without ever storing the raw data points. Another critical engineering design decision is how to handle missing data values, which are inevitable in production pipelines. We have 2 primary strategies: deletion or imputation. Listwise deletion, which involves discarding any record containing a missing value, is simple but dangerous. It can discard valuable data and introduce severe selection bias if the missingness is not completely random. Imputation involves filling in the missing values. The simplest method is mean or median imputation, where we replace missing values with the average of the observed values for that feature. While computationally cheap, mean imputation artificially reduces the variance of the variable, squeezing the probability distribution toward the center and creating an artificial spike at the mean. More advanced methods, such as k-nearest neighbors imputation or multiple imputation by chained equations, which we call mice, estimate the missing value based on the values of other features. While these methods preserve the statistical distribution of the data, they require significant compute resources and introduce the risk of data leakage if the imputation is performed before splitting the dataset into training and validation folds. To see how these concepts are applied in a real-world environment, let us study a production data profiling pipeline for a ride-sharing service. The service logs millions of trips daily, recording features like trip distance, pickup time, traffic delay, and the final fare price. These features are fed into downstream pricing and arrival time models. Before these features can be used, the data profiling pipeline must validate their quality. The engineering team implements Welford's algorithm in a streaming data processor to calculate the running mean and standard deviation of trip durations and fares. If the standard deviation of fares spikes suddenly, it indicates a potential data corruption issue or an extreme weather event that is skewing the pricing dynamics. To identify outliers, such as trips with anomalous fares caused by GPS tracking failures, the pipeline calculates the IQR of the trip fare distribution. Any trip with a fare that lies more than 1.5 times the IQR above the third quartile or below the first quartile is flagged as an outlier. These outliers are excluded from the training set of the pricing model to prevent them from distorting the estimated pricing surfaces. For missing values, such as missing GPS coordinates caused by tunnel signal loss, the system uses spatial imputation, replacing the missing coordinates with the median coordinate of trips originating from the same neighborhood within the same hour, preserving the integrity of the downstream ETA models. Troubleshooting and debugging statistical summaries requires understanding the limits of numerical metrics. A classic warning against relying solely on descriptive statistics is Anscombe's quartet. Anscombe's quartet is a collection of 4 datasets, each containing 11 coordinate pairs. If you calculate the descriptive statistics for these 4 datasets, they appear identical. They have the same mean for both x and y, the same variance, the same correlation coefficient, and the same linear regression line. However, when you plot them, their spatial structures are completely different. One dataset is a linear trend with random noise, another is a perfect parabolic curve, the third is a straight line with a single outlier, and the fourth is a vertical line with one extreme outlier. Another modern illustration of this phenomenon is the Datasaurus dozen. The Datasaurus dozen consists of 12 distinct datasets that also share identical summary statistics, including mean, standard deviation, and correlation. Yet, when plotted, one dataset appears as a Tyrannosaurus rex dinosaur, another as a star, another as a circle, and others as various geometric shapes. Anscombe's quartet and the Datasaurus dozen prove that summary statistics can hide the true structure of your data. To prevent these silent failures in production pipelines, you must implement automated profiling tools that monitor the shapes of your distributions. You can debug drift by setting up telemetry that calculates the Kolmogorov-Smirnov statistic or the population stability index on incoming features. These metrics compare the cumulative distribution function of your production data to your training baseline. If the distribution shape shifts, for example, if a feature's distribution changes from a single bell curve to a double-peaked bimodal distribution due to a new user segment, the monitoring pipeline will trigger an alert. By visualizing your distributions using automated box plots and histograms generated in validation reports, you can detect these structural changes early, ensuring that your statistical learning models are trained on data that matches the operational reality. To expand our pre-processing toolkit, we must also understand robust scaling, which is a key alternative to standardization. While standardization scales features using the mean and standard deviation, it is sensitive to extreme outliers because the mean and standard deviation are themselves highly sensitive to outliers. Robust scaling, instead, scales features by subtracting the median and dividing by the interquartile range. Because both the median and the IQR are robust statistics, robust scaling centers and scales the features without being distorted by extreme values. Spatially, robust scaling ensures that the middle 50% of our data points are mapped to a consistent central region, while outliers are left in the tails, preventing them from dominating downstream model training. We must also analyze how we perform multivariate exploratory data analysis to identify collinearity. Collinearity occurs when 2 or more feature variables are highly correlated with one another, meaning they contain redundant information. Spatially, if we plot 2 collinear features on a scatter plot, the data points will lie almost perfectly along a straight diagonal line. This redundancy makes it difficult for linear models to estimate the individual impact of each feature, leading to high variance in the parameter weights. To identify collinearity during exploratory data analysis, engineers calculate a correlation matrix, which contains the Pearson correlation coefficient for every pair of features in the dataset. We visualize this matrix using a heat map, where colors represent the strength and direction of the correlations. If we identify highly correlated pairs, such as user height in inches and height in centimeters, we remove one of the features, keeping our feature space compact and protecting our models from numerical instability. To systematically profile datasets in automated pipelines, engineers use data quality validation frameworks. When new data streams arrive in a production warehouse, running manual plots is impossible. Instead, we write validation schemas that assert the statistical properties of the incoming data. We define ranges for the mean, standard deviation, and missing value rates, and assert that the distribution shapes match our baselines. If a data stream fails these assertions, for instance, if the missing value rate on a critical feature jumps from 1% to 10% due to a logging bug, the pipeline immediately halts, preventing the corrupted data from reaching our training or inference systems, and ensuring the reliability of our production data pipelines. To understand why we calculate sample variance differently from population variance, we must examine Bessel's correction. When we calculate the variance of an entire population, we divide the sum of squared differences by the total number of observations n. However, when we calculate the variance of a sample, we divide by n-1. This adjustment is called Bessel's correction. We must use n-1 because the sample mean is calculated from the same data points we are analyzing, which mathematically constrains the deviations. The sum of squared deviations from the sample mean is always smaller than the sum of squared deviations from the true, unobservable population mean. Dividing by n instead of n-1 would systematically underestimate the population variance, introducing a negative bias. By dividing by n-1, we correct this bias, obtaining an unbiased estimate of the population variance. We must also recognize that a single mean and standard deviation fail to describe multimodal distributions, where the data contains multiple subpopulations. For example, if you measure the heights of a mixed group of men and women, the distribution of heights will display two distinct peaks, representing a bimodal distribution. Calculating the mean of this bimodal distribution will yield a value that lies in the valley between the two peaks, a height that represents very few individuals in either group. The standard deviation will also be artificially inflated, masking the tight variance within each subpopulation. To debug and analyze multimodal distributions during exploratory data analysis, engineers must use clustering or mixture models like Gaussian mixture models to segment the data into its constituent unimodal components, ensuring that downstream models are trained on homogeneous subsets. To transition from merely describing the data we have to making valid scientific claims about the world, we must enter the domain of inferential statistics. In descriptive statistics, we summarize the properties of our specific training dataset. However, in machine learning, we are almost never interested in only the training data itself. We want to know if the patterns we observe in our sample will hold true in the wider population of future users, transactions, or signals. Inferential statistics is the mathematical framework that allows us to draw generalized conclusions about an unobservable population using a limited, random sample, providing the foundational principles for hypothesis testing, model evaluation, and A/B testing. Let us begin by clarifying the distinction between a population and a sample. The population represents the entire, complete collection of all possible observations we could make. If we are building a model to predict user behavior, the population is every user who will ever visit our website in the future. The population is infinitely large and fundamentally unobservable in its entirety. The sample, conversely, is the specific subset of the population that we have actually observed and recorded in our training database. Spatially, you can visualize the population as a vast, deep ocean of potential data points, and our sample as a single bucket of water scooped out of that ocean. Inferential statistics is the science of analyzing the contents of our bucket to make mathematically precise statements about the chemical composition of the entire ocean. To perform this inference, we must distinguish between standard deviation and standard error. Standard deviation measures the dispersion or spread of individual data points within a single sample or the population. It tells us how much individual observations vary around their average. Standard error, on the other hand, measures the precision of our sample estimate. Specifically, the standard error is the standard deviation of the sampling distribution of our estimator, the theoretical distribution we would obtain if we drew infinitely many samples of size n and calculated their statistics. The standard error represents how much our sample mean is expected to fluctuate from one sample to the next. Mathematically, standard error is equal to the standard deviation divided by the square root of the sample size n. As n increases, the standard error shrinks, reflecting the increased precision of our estimates. The mathematical engine that makes this possible is the central limit theorem. The central limit theorem states that if you draw random, independent samples of size n from any population distribution regardless of its shape, and calculate the mean of each sample, the distribution of those sample means will shape into a normal Gaussian bell curve as the sample size n grows. The mean of this normal distribution of sample means will be exactly equal to the true population mean, and its standard deviation, which we call the standard error, will be equal to the population standard deviation divided by the square root of n. Spatially, this means that even if our raw population distribution is highly skewed, bimodal, or flat, the distribution of our sample averages will become increasingly narrow and symmetric around the true population parameter as we collect larger samples, allowing us to use normal probability calculations to evaluate our estimations. Hypothesis testing is the formal procedure we use to determine whether an observed effect in our sample is statistically significant or merely a random coincidence. We begin by defining two competing claims: the null hypothesis and the alternative hypothesis. The null hypothesis, represented as H0, is the conservative assumption that there is no effect, no difference, or no relationship between our variables. Spatially, in a regression model, the null hypothesis assumes that the slope of our estimated surface is completely flat, meaning our inputs have zero systematic effect on the output. The alternative hypothesis, HA, is the claim that there is a real effect, a non-zero difference, or a sloping relationship. To evaluate these hypotheses, we must balance two types of errors, which we define as type 1 and type 2 errors. A type 1 error, represented by the Greek letter alpha, occurs when we incorrectly reject a true null hypothesis, also known as a false positive. A type 2 error, represented by the Greek letter beta, occurs when we fail to reject a false null hypothesis, also known as a false negative. Statistical power, calculated as 1 minus beta, is the probability of correctly rejecting the null hypothesis when a real effect exists. Spatially, imagine two overlapping normal distribution curves plotted on a horizontal axis representing our test statistic. The curve on the left represents the probability distribution under the null hypothesis, and the curve on the right represents the distribution under the alternative hypothesis. We place a vertical decision boundary between them. Any test statistic that falls to the right of this boundary leads us to reject the null hypothesis. The area under the null curve to the right of the boundary represents alpha, the false positive rate. The area under the alternative curve to the left of the boundary represents beta, the false negative rate. If we move the decision boundary to the right to decrease alpha and minimize false positives, we automatically increase the area of beta, which lowers our statistical power. To decrease both error rates simultaneously, we must collect larger samples, which narrows both curves and reduces their overlap. To choose between these hypotheses, we calculate a test statistic from our sample data, such as a t-statistic, and use it to determine a p-value. The p-value is the probability of obtaining a test statistic at least as extreme as the one we observed, assuming that the null hypothesis is true. Spatially, if you plot the probability distribution curve of the test statistic under the assumption that the null hypothesis is correct, the p-value represents the area under the tails of that curve starting from our observed value. A small p-value, typically less than 0.05, indicates that our observed sample is highly anomalous if the null hypothesis is true. This leads us to reject the null hypothesis in favor of the alternative. A confidence interval represents the range of values within which the true population parameter is expected to lie, calculated at a specific confidence level, such as 95%, which mathematically means that if we repeat our sampling process thousands of times, 95% of the calculated intervals will contain the true parameter. Transitioning to engineering design decisions, these statistical concepts are the foundation of product experimentation, commonly known as a B testing. When an engineering team wants to deploy a new feature, they must prove that it improves key business metrics such as click rate or conversion value. To design a valid A/B test, engineers must run a power analysis to calculate the required sample size before launching the experiment. The power analysis depends on three parameters: the significance level alpha, which is the probability of committing a false positive; the statistical power, which is the probability of correctly detecting a real effect; and the minimum detectable effect, which we refer to as the MDE. The MDE represents the smallest change in the metric that is economically meaningful to the business. Choosing a very small MDE requires a massive sample size, creating a direct engineering trade-off. Running an experiment with a small MDE requires routing millions of users through the testing pipeline, increasing compute costs and extending the experiment's duration, which slows down the product release cycle. Another major engineering challenge in online experimentation is the multiple testing problem. If you run a single hypothesis test at a significance level of 0.05, you have a 5% chance of finding a significant result by pure random chance, which is a false positive. If your experimentation dashboard tracks 20 different metrics simultaneously, such as bounce rate, page load time, search clicks, and signups, the probability of detecting at least one false positive by pure chance spikes to approximately 64%. To prevent this look elsewhere effect from corrupting your product decisions, engineers must implement corrections. The most conservative solution is the Bonferroni correction, which involves dividing the target significance level by the number of metrics tested. Alternatively, you can use the Benjamini-Hochberg procedure to control the false discovery rate, which adjusts the significance thresholds dynamically to balance the rate of false discoveries against the power to detect real improvements. To see these principles in a real-world scenario, let us study a production case study of an e-commerce platform testing a new machine learning algorithm for product recommendations. The team wants to determine if the new algorithm increases the average checkout value per user compared to the existing baseline algorithm. The engineering team begins by estimating the baseline variance of checkout values using historical transaction logs. They define their null hypothesis as stating that the mean checkout value of users served by the new algorithm is equal to the mean checkout value of users served by the baseline algorithm. They set their significance level to 0.05 and their power target to 80%, deciding that they want to detect a minimum detectable effect of a 1% increase in average checkout value. Using these parameters, the power analysis dictates that they must assign 100,000 users to the control group, which receives the baseline recommendations, and another 100,000 users to the treatment group, which receives the new recommendations. The system uses a consistent hashing service to map incoming user IDs to either the control or treatment bucket, ensuring that a user consistently experiences the same recommender algorithm throughout the experiment. As transactions occur, the system streams the checkout values into a database. Once the target sample size is reached, the analysis service runs a two-sample t-test. The test compares the sample mean checkout value of the control group to that of the treatment group, calculating a t-statistic. The resulting p-value is 0.012, which lies below the significance threshold. The system also calculates a 95% confidence interval for the difference in means, which ranges from 0.2% to 1.8%. Because the p-value is significant and the confidence interval is entirely positive, the engineering team confidently rejects the null hypothesis and rolls out the new recommender algorithm to the entire user base. Troubleshooting and debugging statistical experiments in production requires guarding against common operational pitfalls, starting with the peaking problem. The peaking problem occurs when engineers monitor the p-value of an ongoing experiment daily and stop the test early the moment the p-value dips below 0.05. Because sample statistics fluctuate naturally over time, the p-value will occasionally cross the significance boundary by pure chance. Stopping the test the moment this happens is a form of selection bias known as p-hacking, which inflates the actual false positive rate from 5% to over 30%, leading to the deployment of ineffective or harmful features. To debug and prevent the peaking problem, engineers must enforce strict sample size targets, allowing the experiment to run until the pre-calculated sample size is fully met before performing the statistical test, or use sequential testing frameworks that adjust the significance boundaries dynamically over time. Another critical failure mode is sample ratio mismatch, which we refer to as SRM. SRM occurs when the actual proportion of users observed in the control and treatment groups deviates significantly from the designed allocation ratio. For example, if you design a 50-50 split, but your database records 99,000 users in control and 101,000 users in treatment, this difference might seem minor. However, running a chi-square goodness of fit test on these counts yields a p-value of near zero, indicating that the mismatch is highly unlikely to have occurred by chance. SRM is a diagnostic signature of allocation bias, indicating that one group is systematically dropping users or failing to log events. This can happen if the new algorithm increases page load latency, causing mobile users with slow connections to abandon the page before their telemetry event is logged. To debug SRM, engineers must audit the event routing pipeline. They must trace the user assignment flow step by step, verifying that the hashing algorithm is uniform and that telemetry events are logged before any experimental treatment is applied. By building automated SRM checks into your experimentation dashboards that raise alerts when the chi-square p-value drops below 0.001, you can catch telemetry and routing bugs early, preserving the scientific validity of your production experiments. To expand our experimental capabilities, we must look at statistical tests that compare 3 or more groups simultaneously, which introduces analysis of variance, commonly referred to as ANOVA. If we want to test 3 different recommendation algorithms, running multiple pairwise t-tests is an engineering anti-pattern. If we run 3 separate t-tests, each at a significance level of 0.05, our family-wise error rate, the probability of committing at least one false positive spikes to 14%. ANOVA resolves this by evaluating the variance between the group means relative to the variance within the groups, calculating an F-statistic. If the F-statistic is significant, It proves that at least one group mean is different from the others, allowing us to subsequently run post hoc tests to locate the best algorithm while controlling our false positive rates. We must also understand when to use non-parametric hypothesis tests, which are essential when our data violates the assumption of normality. Standard t-tests assume that the response variable is normally distributed within each group. If we are testing highly skewed metrics, such as user session durations or transaction values, these normality assumptions fail. In such scenarios, running a t-test can yield misleading results. Instead, we use non-parametric tests like the Mann-Whitney U-test or the Wilcoxon sign rank test. These tests do not assume a specific probability distribution shape. Instead, they rank the observations and perform calculations on the ranks, providing a robust and mathematically valid evaluation of skewed or heavy-tailed data. To implement multiple testing corrections dynamically in our dashboards, we use the Benjamini-Hochberg procedure to control the false discovery rate. While the Bonferroni correction is simple and divides alpha by the number of tests, it is often too conservative. It lowers the significance threshold so much that the statistical power collapses, making it almost impossible to detect real product improvements. The Benjamini-Hochberg procedure, by contrast, sorts the p-values of all tests in ascending order and compares them to a sliding threshold that scales with the rank of the test. This adaptive scaling controls the proportion of false positives among the rejected hypotheses while preserving statistical power, allowing engineers to track multiple metrics without sacrificing the ability to ship product updates. To ensure that our experimental results translate into real-world business value, we must distinguish between statistical significance and practical significance. Statistical significance, which is determined by a p-value falling below our alpha threshold, simply proves that the observed difference between our groups is unlikely to have occurred by chance. It does not measure the size or importance of that difference. If our sample size is large enough, containing millions of users, even a microscopic, economically meaningless difference, such as a 0.001% increase in conversion rate, will yield a statistically significant p-value. To evaluate whether an effect is practically significant, engineers must analyze the effect size and look at the confidence intervals, verifying that the lower bound of the estimated improvement exceeds the operational cost of deploying and maintaining the new model. To understand how machine learning models actually learn from data, we must explore the mathematical engine of optimization, which is built entirely on the principles of calculus. When we train a model, we define a loss function that measures the discrepancy between our model's predictions and the actual target values. The goal of training is to find the specific set of parameters that minimizes this loss function. Calculus is the mathematical tool that tells us how to adjust our parameters to decrease the loss, acting as a steering wheel that guides our model toward the optimal solution. By mastering the spatial concepts of derivatives, partial derivatives, gradients, and gradient descent, you can understand how models navigate complex cost landscapes to find the valley of minimum error. Let us start with the concept of the derivative, which represents the instantaneous rate of change of a function. In simple terms, the derivative tells us how much the output of a function will change in response to a tiny change in its input. Spatially, if you plot a curve on a two-dimensional graph, the derivative at any given point is the slope of the tangent line that touches the curve at exactly that point. If the slope is positive, it means increasing the input will increase the output. If the slope is negative, increasing the input will decrease the output. If the slope is 0, it indicates a flat point, which could be a local minimum, a local maximum, or a saddle point. The derivative represents a first-order linear approximation of the function near that point. To understand the curvature of our loss surface, we must look to the second derivative. While the first derivative tells us the slope of the line, the second derivative measures the rate of change of that slope, representing the curvature of the function. Spatially, if the second derivative is positive, the function is convex, curving upward like a bowl. If it is negative, the function is concave, curving downward. In multidimensional spaces, we group these second-order partial derivatives into a square matrix called the Hessian matrix. The Hessian describes the local geometry of our loss surface. Spatially, the eigenvalues of the Hessian tell us the nature of our critical points. If all the eigenvalues of the Hessian are positive, the curvature is upward in all directions, indicating a local minimum. If all eigenvalues are negative, the curvature is downward in all directions, representing a local maximum. If some eigenvalues are positive and others are negative, we are at a saddle point, a region that looks like a pass between two mountain peaks, curving upward in one direction and downward in another. In machine learning, our loss functions depend on millions of parameters simultaneously, requiring us to extend the concept of the derivative to multidimensional spaces using partial derivatives. A partial derivative measures the rate of change of a function with respect to one specific variable, while holding all other variables constant. If we group all the partial derivatives of our loss function with respect to every single parameter into a single vector, we obtain the gradient. Spatially, you can visualize the gradient as a vector pointing in the direction of the steepest descent on a multidimensional terrain. The magnitude of the gradient vector represents the slope of that ascent. Therefore, if we want to minimize our loss function, we must move in the opposite direction of the gradient, the direction of steepest descent. This brings us to gradient descent, the primary optimization algorithm in machine learning. Spatially, imagine you are standing on a foggy mountain peak at night, and your goal is to find the lowest valley. Because of the fog, you cannot see the path down the mountain. You can only feel the slope of the ground beneath your feet. To make progress, you determine the direction of the steepest downward slope and take a step in that direction. You repeat this process at each step. Evaluate the local slope, take a step downward, and reassess. In our optimization framework, the mountain peak represents a high loss value, the steps represent parameter updates, the direction beneath your feet is the negative gradient, and the lowest valley represents the parameter configuration that minimizes our loss. The size of the step we take at each iteration is controlled by a hyperparameter known as the learning rate or step size. Choosing the learning rate is a critical engineering decision. If the learning rate is too small, our model will take tiny steps, requiring millions of iterations to reach the bottom of the valley, which translates to high compute costs and long training times. If the learning rate is too large, the model will take giant leaps, overshooting the bottom of the valley and climbing up the opposite slope. This can cause the optimization process to oscillate wildly or diverge entirely, sending the loss values to infinity. Transitioning to engineering design decisions, how we compute these gradients over large-scale datasets introduces major trade-offs in memory alignment and compute efficiency. In batch gradient descent, we compute the gradient of the loss function over the entire dataset before making a single parameter update. While this provides a highly stable and mathematically precise step direction, it is computationally impractical for production datasets containing billions of samples. The memory footprint required to store all observations simultaneously exceeds the capacity of modern hardware, and computing a single update takes hours. To accelerate optimization, engineers use stochastic gradient descent, which we refer to as SGD or mini-batch gradient descent. In SGD, we update the parameters based on the gradient computed from a single, randomly selected training example. This makes each step incredibly fast and requires virtually no memory. However, because individual data points contain noise, the trajectory of SGD is highly erratic, bouncing wildly across the loss surface. Mini-batch gradient descent represents the industry standard compromise. We compute the gradient over a small, random subset of the data, which we call a mini-batch. To optimize compute performance, engineers select mini-batch sizes that are powers of 2, such as 64, 128, or 256. This choice aligns with the memory hierarchy of GPUs, allowing the hardware to perform coalesced memory accesses and maximize the parallel processing throughput of the vector cores. To compute these gradients in modern software frameworks, engineers rely on automatic differentiation rather than manual symbolic calculation or numerical approximation. Numerical differentiation, which estimates gradients by adding a tiny value h to each parameter and recalculating the loss, is an engineering anti-pattern for large models. It requires O of p forward passes of the network, where p is the number of parameters, making it computationally prohibitive. It is also numerically unstable due to floating-point round-off errors. Automatic differentiation, specifically reverse-mode automatic differentiation, builds a dynamic computational graph of operations during the forward pass. During the backward pass, the system applies the chain rule of calculus to compute all partial derivatives in a single backward pass, regardless of the number of parameters. This reverse-mode traversal reduces the computational complexity of gradient calculation to constant time relative to the number of features, enabling the training of models with billions of parameters. To further stabilize optimization, engineers use advanced optimizers like ADAM, which stands for Adaptive Moment Estimation. ADAM enhances standard gradient descent by tracking moving averages of both the gradients, which represents momentum, and the squared gradients, which represents the variance of the gradients. Momentum helps the optimizer push through flat regions and saddle points by accumulating velocity in consistent directions. The variance term scales the learning rate for each parameter individually, performing larger updates for features that receive infrequent updates and smaller updates for features that oscillate wildly. This adaptive scaling allows ADAM to navigate complex, non-convex loss surfaces efficiently, reducing training times significantly. To see these concepts in action, let us study a production case study involving the training of a deep learning recommendation model for a video streaming platform. The platform's neural network features millions of weights, and it is trained using binary cross-entropy loss to predict whether a user will watch a suggested video. The loss surface of a neural network of this scale is highly non-convex, filled with millions of local minima, flat plateaus, and saddle points. If the engineering team trains the model using standard stochastic gradient descent, the optimization process will quickly stall on a saddle point, a flat region where the gradient is zero but which is not a true minimum. The model will stop learning, resulting in poor recommendation accuracy. To resolve this, the team configures their training pipeline to use the ADAM optimizer with a mini-batch size of 256. They distribute the computation across a cluster of GPUs. During the training run, the GPU cores load a mini-batch, run a forward pass to calculate the predictions, and run a backward pass using automatic differentiation to compute the partial derivatives of the loss with respect to every weight. The ADAM optimizer processes these gradients, applying momentum to guide the parameter updates through the flat saddle points, and adjusting the learning rate for sparse features like rare video IDs. By using calculus to navigate this complex space, the platform trains the network to convergence in a few hours, yielding highly accurate recommendations. Troubleshooting and debugging calculus-based optimization pipelines requires detecting and resolving numerical stability issues, which commonly manifest as vanishing or exploding gradients. These failures occur during backpropagation, where gradients are multiplied repeatedly across the layers of a deep network. If the weights of your network are initialized to values that are too large, the gradients can grow exponentially as they travel backward through the layers. This is the exploding gradient problem. When this occurs, the parameter updates become massive, causing the weights to overflow and resulting in numerical not a number or NaN values in your training logs. The model's learning collapses. To debug exploding gradients, engineers implement gradient clipping. Gradient clipping sets a maximum threshold for the norm of the gradient vector. If the gradient norm exceeds this threshold during training, the vector is scaled down to the limit, preventing parameter updates from becoming too large. The vanishing gradient problem represents the opposite failure mode. If your weights are initialized to values that are too small, or if you use activation functions like the sigmoid function that saturate at extreme values, the gradients will shrink exponentially as they propagate backward. By the time the gradient reaches the early layers of the network, its value is virtually zero, and these early layers stop learning. To debug vanishing gradients, engineers use weight initialization strategies like Xavier or He initialization, which mathematically scale the initial weights based on the number of input and output units to preserve variance across layers. They also replace saturating activation functions with rectified linear units and implement batch normalization layers to normalize inputs within each mini-batch, ensuring that gradients flow smoothly through the network and stabilizing the training pipeline. By logging gradient norms and monitoring weight histograms in your telemetry dashboards, you can detect these numerical failures early, ensuring the stability of your optimization loops. To understand more advanced optimization techniques, we must examine second-order optimization methods, which use both the gradient and the Hessian matrix to update parameters. The classic second-order method is the Newton-Raphson method, which updates parameters by multiplying the gradient by the inverse of the Hessian matrix. Spatially, while gradient descent performs a linear approximation and takes a step in the direction of the local slope, Newton's method performs a quadratic approximation, fitting a multidimensional paraboloid to the local curvature and stepping directly to its minimum. This quadratic approximation allows second-order methods to converge in far fewer steps than standard gradient descent, especially near the minimum where the curvature is stable. However, the computational cost of inverting a Hessian matrix of size p by p is O of p cubed, which is prohibitively expensive for models with millions of parameters. To make second-order optimization practical, engineers use quasi-Newton methods like BFGS and its memory-limited variant LBFGS, which approximate the inverse Hessian incrementally using only gradient information, reducing the memory footprint and compute cost. We must also manage the learning rate schedule over the course of training using decay techniques. Holding the learning rate constant throughout training is rarely optimal. Early in training, we want a large learning rate to quickly move down the steep slopes of the loss surface. As we approach the minimum, a large learning rate will cause the model to overshoot, so we want to decay the step size. Engineers implement learning rate schedulers, such as cosine annealing or step decay, to decrease the learning rate systematically over time. In cosine annealing, the learning rate decays along a cosine curve, starting high, dropping to near zero, and occasionally warm restarting back to a high value. Warm restarts allow the model to escape local minima and explore different regions of the lost surface, improving the probability of finding a global minimum and stabilizing model training. To understand the difference between local and global minima, we must explore the concept of convexity. A loss function is convex if any 2 points on its surface can be connected by a straight line that lies entirely above or on the surface. Convex loss functions, like the mean squared error in linear regression, have a single local minimum that is also the global minimum. This guarantees that gradient descent will always converge to the optimal solution. Non-convex loss functions, which are common in deep learning, have complex surfaces with many local minima, peaks, and saddle points. Gradient descent is not guaranteed to find the global minimum in non-convex spaces, which is why initialization strategies, batch normalization, and adaptive optimizers are essential to guide the model toward high-quality local minima. To automate the search for the optimal step size at each iteration of gradient descent, engineers use backtracking line search. Selecting a fixed learning rate is a risky engineering choice, as the slope of the lost surface changes continuously. Backtracking line search resolves this by starting with a relatively large learning rate and systematically reducing it by a scaling factor until the step satisfies the Armijo condition. The Armijo condition mathematically guarantees that the step achieves a sufficient decrease in the loss function relative to the gradient magnitude. By dynamically adjusting the learning rate at each step, backtracking line search ensures that the optimizer takes large steps on flat plateaus and automatically takes smaller steps in steep valleys, preventing divergence and accelerating convergence without manual hyperparameter tuning. Let us analyze how the vanishing gradient problem occurs in deep networks through the mathematical lens of the chain rule. During backpropagation, the gradient of the loss with respect to a weight in an early layer is calculated by multiplying the derivatives of the activation functions of all subsequent layers. If we use the sigmoid activation function, its derivative has a maximum value of only 0.25. When we multiply these derivatives across 10 layers, the gradient is scaled by a factor of 0.25 raised to the power of 10. Which is approximately 1 in 1 million. This repeated multiplication of values less than 1 causes the gradient to decay exponentially as it propagates backward, reducing the parameter updates in the early layers to 0. By understanding this mathematical multiplication, engineers can see why replacing sigmoids with rectified linear units, which have a derivative of 1 for all positive values, is mathematically necessary to prevent gradients from vanishing in deep networks. To verify that our optimization efforts have yielded a model that can perform in the real world, we must establish a rigorous framework for assessing model accuracy. In our study of gradient descent, we focused on minimizing the loss function on our training data. However, as we have learned from the hazards of overfitting, training performance is a highly deceptive guide. We must evaluate our models on independent validation datasets using metrics that align with both mathematical rigor and business objectives. Model evaluation is not merely the final step in the training pipeline. It is a continuous feedback loop that dictates whether a model is safe to deploy, how it compares to alternative architectures, and when it requires retraining in production. Let us start by exploring the metrics we use to evaluate regression models, where the target variable is continuous. The most fundamental metric is the mean squared error, or MSE. To calculate the MSE, we measure the vertical distance between each actual data point and our estimated model surface, square these distances to eliminate negative signs and penalize larger errors, and average the results. Because the MSE is expressed in squared units, we often take its square root to calculate the root mean squared error, or RMSE. The RMSE is highly interpretable because it is expressed in the same physical units as our target variable, such as dollars, degrees, or meters, representing the average deviation of our predictions. While the RMSE is mathematically convenient and aligns with the loss functions of many optimizers, its sensitivity to outliers can sometimes distort our evaluation. If a model predicts 99 points perfectly but misses a single point by a massive margin, the squared error term for that outlier will dominate the RMSE, making a generally excellent model appear poor. To mitigate this outlier sensitivity, engineers use the mean absolute error, or MAE. The MAE calculates the average of the absolute differences between the predictions and the actual values, placing a linear penalty on all errors. Spatially, while the RMSE pulls our estimated surface toward extreme points to avoid large squared penalties, the MAE finds the median trajectory, remaining robust against isolated anomalies. The R-squared statistic, also known as the coefficient of determination, provides a normalized measure of regression performance. Instead of expressing error in physical units, R-squared measures the proportion of variance in the response variable y that can be explained by our features x. Spatially, imagine a baseline model that represents a flat, horizontal plane fixed at the mean value of y. This baseline model represents a scenario where we have 0 predictive features, and its squared error is the total sum of squares. When we fit our statistical model, we measure its residual sum of squares. The R-squared statistic is calculated as 1 minus the ratio of the residual sum of squares to the total sum of squares. A value of 1 indicates that our model explains all the variance, fitting the data perfectly, while a value of 0 indicates that our model performs no better than simply predicting the mean. Classification models, where the target variable represents discrete categories, require a completely different set of evaluation metrics based on the confusion matrix. A confusion matrix is a two-dimensional grid that cross-references the actual class labels against our model's predicted class labels. This grid defines 4 possible outcomes for a binary classification task. True positives represent cases where the model correctly predicted the positive class. True negatives represent cases where the model correctly predicted the negative class. False positives, also known as type 1 errors, occur when the model incorrectly predicts the positive class when the actual label is negative. False negatives, also known as type 2 errors, occur when the model incorrectly predicts the negative class when the actual label is positive. The most intuitive classification metric is accuracy, which is the sum of true positives and true negatives divided by the total number of observations. While accuracy is simple to understand, it is a dangerous metric to use when dealing with imbalanced datasets. Consider a fraud detection system where only 1 out of every 1,000 transactions is fraudulent. A naive model that simply predicts that every transaction is legitimate will achieve 99.9% accuracy. However, this model is completely useless because it fails to catch a single fraudulent event. To evaluate imbalanced systems effectively, engineers rely on precision and recall. Precision is the ratio of true positives to the total number of positive predictions. Precision measures the model's reliability when it makes a positive claim. Spatially, precision answers the question, of all the points the model placed inside the positive boundary, what fraction actually belongs there? Recall, also known as sensitivity or the true positive rate, is the ratio of true positives to the total number of actual positive cases in the dataset. Recall measures the model's ability to find all the positive cases. To visualize the trade-off between precision and recall, imagine a fisherman trying to catch a specific species of fish in a lake. If the fisherman casts a massive, fine mesh net across the entire lake, they will catch every single target fish in the water, achieving 100% recall. However, the net will also collect debris, boots, and non-target species, resulting in extremely low precision. If the fisherman uses a spear and only strikes when they are absolutely certain they see a target fish, they will achieve high precision, but they will miss many other fish in the lake, resulting in low recall. The F1 score represents the harmonic mean of precision and recall, providing a single metric that balances both forces, which is particularly useful when optimizing class-imbalanced models. To evaluate classification performance across all possible decision thresholds, we use the receiver operating characteristic curve, which we refer to as the ROC curve. The ROC curve plots the true positive rate on the vertical axis against the false positive rate on the horizontal axis across every threshold from 0 to 1. The false positive rate is calculated as false positives divided by the sum of false positives and true negatives. The area under the ROC curve, or OROC, provides a single metric summarizing classifier performance. An OROC of 1.0 represents a perfect model, while an OROC of 0.5 represents a model that performs no better than pure random guessing, represented as a diagonal line across the space. Choosing between OROC and the area under the precision recall curve, or AUPRC, is a critical engineering decision. OROC can be misleadingly optimistic when evaluating datasets with extreme class imbalance. Because the denominator of the false positive rate contains true negatives, a massive negative class will keep the false positive rate artificially close to 0, even if the model predicts thousands of false positives. AUPRC, by contrast, does not include true negatives in its calculations, focusing exclusively on true positives, false positives, and false negatives. Therefore, on highly imbalanced datasets, AUPRC provides a much more honest and sensitive measure of model performance, reflecting the real impact of false positives on the system. For multi-class classification tasks, we must decide how to aggregate our metrics using micro, macro, or weighted averaging. Micro-averaging pools the true positives, false positives, and false negatives across all classes to calculate a single global metric. This approach is dominated by the most frequent classes. Macro-averaging calculates the precision and recall for each class independently and averages the results equally. Macro-averaging treats all classes equally, making it highly sensitive to the performance of rare classes. Weighted averaging calculates class-specific metrics and averages them weighted by the number of true samples in each class, balancing the class frequencies with individual performance. Transitioning to engineering design decisions, the choice of evaluation metric must be driven by the specific operational costs of the business. Engineers must ask themselves, is a false positive more expensive than a false negative? Or is it the other way around? In a medical screening pipeline, a false negative is catastrophic because a patient with a life-threatening disease will be sent home without treatment. A false positive, which results in a healthy patient being scheduled for further tests, is stressful and expensive but not fatal. Therefore, medical systems prioritize recall, setting low decision thresholds to ensure no positive case is missed. Conversely, in a spam filter, a false positive means a critical business email is diverted to the spam folder where it may never be read, while a second-tier newsletter slipping into the inbox is merely a minor annoyance. Spam filters prioritize precision, setting high decision thresholds to ensure that any email flagged as spam is classified with absolute certainty. To see these principles applied in production, let us study the case study of a content moderation system for a high-traffic social media platform. The system's goal is to detect and flag posts that violate the platform's safety policies. The dataset is highly imbalanced, as only 0.5% of all posts contain violations. For this system, the engineering team cannot use accuracy to evaluate performance. They also cannot rely on a single decision threshold. Instead, they evaluate their models using the AUPRC, which plots precision on the vertical axis against recall on the horizontal axis across every possible decision threshold, measuring the model's performance independently of the specific threshold chosen. To deploy this model safely, the team implements a multi-tier threshold architecture based on the business costs. For posts where the model's confidence exceeds a high-precision threshold of 99%, the system automatically deletes the content, minimizing the risk of accidentally censoring legitimate users. For posts where the confidence lies between 70% and 99%, the system routes the content to human reviewers for manual inspection, prioritizing recall to ensure borderline violations are caught. By selecting and configuring evaluation metrics based on operational costs, the platform balances user safety with content integrity. Troubleshooting and debugging model evaluation pipelines requires preventing metric leakage and threshold drift. Metric leakage occurs when evaluation metrics are computed on validation datasets that have been contaminated by the training process. For example, if you normalize your features or impute missing values using the mean of the entire dataset before splitting it into training and validation sets, the validation set will contain subtle statistical information about the training set. This leakage will cause your validation metrics to look artificially optimistic, masking generalization failures that will emerge immediately after deployment. To debug metric leakage, engineers must construct strict data pipeline boundaries using framework constructs like scikit-learn pipelines. You must ensure that all pre-processing steps, including scaling, imputation, and feature selection, are fit exclusively on the training fold and applied as a transform to the validation fold without updating the statistics. Threshold drift represents another critical production challenge. When a model outputs a probability, we convert it into a binary classification by comparing it to a decision threshold. The optimal threshold is typically selected offline using a validation set. However, in production, the base rate of the positive class can shift over time due to seasonal behavior or external events. This prior probability shift will invalidate the offline threshold, causing the model to produce unexpected rates of false positives or false negatives. To debug threshold drift, engineers set up continuous calibration monitoring using the Breyer score. The Breyer score measures the mean squared difference between the predicted probabilities and the actual binary outcomes. They log the model's predicted probabilities alongside the actual labels as they are resolved. They plot calibration curves to verify that when the model predicts a 60% probability of an event, it occurs 60% of the time in reality. If the model becomes uncalibrated, they implement isotonic regression or Platt scaling to recalibrate the outputs, or adjust the decision threshold dynamically to maintain the target precision and recall constraints, protecting the production system from silent degradation. To assess classification performance on highly imbalanced datasets, we also use advanced metrics like Cohen's kappa and the Matthews correlation coefficient, which we refer to as MCC. Accuracy can be misleading, and even precision and recall can present an incomplete picture if the classes are highly skewed. Cohen's kappa measures the agreement between the actual and predicted classes while adjusting for the agreement that could occur by pure random chance. The Matthews correlation coefficient is a balanced measure that incorporates all four quadrants of the confusion matrix: true positives, true negatives, false positives, and false negatives. MCC outputs a value between -1 and +1, where +1 represents a perfect prediction, 0 represents random guessing, and -1 represents total disagreement. Because MCC is symmetric and balances class sizes, it provides a highly reliable evaluation of model performance on extreme datasets. We must also understand the role of log loss, also known as cross-entropy loss, as both an evaluation metric and a training objective. Unlike hard classification metrics like accuracy or F1 score, which are calculated on binary predictions, log loss is calculated on the predicted probabilities themselves. Log loss penalizes the model based on its uncertainty. If the model predicts a 99% probability of a positive class, but the actual label is negative, the model is penalized heavily. Mathematically, log loss is the negative logarithm of the predicted probability assigned to the correct class. Evaluating models using log loss is crucial because it measures the quality of the probability calibration. A model can achieve high accuracy by making confident, lucky guesses, but it will exhibit poor log loss if its probability estimates are uncalibrated and overconfident, making log loss an essential metric for risk scoring and underwriting systems. To evaluate regression models on relative error rather than absolute error, engineers use mean absolute percentage error, which we call MAPE. While RMSE and MAE measure error in the physical units of the target variable, they do not scale with the size of the target. An absolute error of $10 is minor if the actual sale value is $10,000, but it is catastrophic if the actual value is $5. MAPE resolves this by dividing the absolute error of each prediction by the actual value, expressing the error as a percentage. However, standard MAPE has a critical mathematical limitation. If the actual value is 0, the division fails, resulting in an undefined value. To resolve this division by 0, engineers use symmetric MAPE, which divides the absolute error by the average of the actual and predicted values, providing a stable, scale-independent metric for forecasting pipelines. To interpret the curves accurately, we must also understand the difference in baseline behaviors between the ROC curve and the precision recall curve. The baseline of an ROC curve is always a diagonal line representing random guessing, which corresponds to an area under the curve of 0.5, regardless of the class distribution. The baseline of a precision recall curve, however, is a horizontal line fixed at the proportion of positive cases in the dataset. If only 0.5% of our samples are positive, the baseline AUPRC of a random classifier is 0.005. This class-dependent baseline means that achieving an AUPRC of 0.7 on a highly imbalanced dataset is an exceptional result, whereas the same score on a balanced dataset would be mediocre, illustrating why we must evaluate AUPRC in the context of the dataset's base rate. To bridge the gap between abstract mathematical concepts and tangible engineering systems, we must explore how these foundations are implemented using the Python programming language. In our previous discussions, we explored linear algebra, probability, calculus, and evaluation metrics as mathematical equations. However, in production, we do not perform these calculations on paper. We write software. Python has emerged as the industry standard language for machine learning, not because it is the fastest executing language, but because it acts as a highly readable coordinator for low-level, high-performance computing libraries. By understanding how Python represents mathematical structures, how data pipelines partition information, and how models are instantiated and trained, you can translate your theoretical mental models into reliable, executable code. Let us first examine why the Python ecosystem is structured the way it is. Python itself is an interpreted language, meaning it executes code line by line, which introduces significant overhead and makes standard Python loops too slow for processing large-scale numerical datasets. Furthermore, Python has historically been constrained by the global interpreter lock, which we refer to as the GIL. The GIL prevents multiple native threads from executing Python bytecodes at once, limiting pure Python multithreading on multi-core processors. To achieve compiled speed and true parallel execution, libraries like NumPy and Pandas bypass the GIL by wrapping low-level libraries written in C, C++, or Fortran. Spatially, when you represent a dataset in NumPy, the data is not stored as a slow, fragmented Python list of objects scattered across system memory. It is stored as a contiguous block of raw binary numbers in RAM. We must understand the memory layout of these arrays, which can be stored in row major order, also known as C-style, or column major order, also known as Fortran style. In row major layout, the elements of a row are stored next to each other in physical memory. This is highly efficient for machine learning models that process observations row by row, as the CPU can load adjacent features into high-speed cache memory, avoiding slow random RAM lookups. This structure allows the hardware to perform vectorized operations, executing a single instruction across an entire array of values simultaneously, which bypasses the interpreter's bottlenecks and utilizes the CPU's vector units at compiled speed. The primary step in any coding pipeline is loading our raw variables and mapping these optimized memory structures. In a typical workflow, we read our data from a structured file, such as a CSV file, into a Pandas data frame. A data frame represents our mathematical matrix, where columns correspond to features and rows correspond to individual observations. Once the data is loaded, we partition it into our mathematical inputs X and our target outputs Y. Spatially, this is equivalent to slicing our data matrix vertically, separating the feature columns from the response column. Before passing these features to our models, we must perform feature scaling, which introduces a critical coding decision: standardization versus min-max scaling. Standardization, also known as z-score normalization, scales a feature so that it has a mean of 0 and a standard deviation of 1. Min-max scaling scales a feature to a fixed range, typically between 0 and 1. Standardization is preferred for gradient-based models like logistic regression or neural networks, as it centers the data and ensures that the loss surface is symmetric, accelerating gradient descent convergence. Min-max scaling is preferred when we need to preserve absolute boundaries, such as scaling image pixel values between 0 and 1. Spatially, scaling is like resizing our coordinate axes. If we fail to scale features with different units, the optimizer will oscillate wildly, as the gradients along the larger scale axis will dominate the weight updates, slowing down convergence. After scaling our features, we must partition the rows of our dataset into a training block and a test block. This train-test split is a crucial engineering practice. The training block, typically containing 80% of the rows, is used to optimize the model's parameters. The test block, containing the remaining 20%, is set aside as an independent validation set. To ensure that this split is random and representative, we use a random number generator. However, to guarantee that our work is reproducible, we must set a random seed, often referred to in code as the random state. Spatially, partitioning the data is like shuffling a deck of cards and dealing them into two piles. If we do not set a random seed, the shuffling process will yield different cards in each pile every time we run the script. This makes it impossible to compare model changes, as a change in performance might be caused by a different data split rather than an algorithmic improvement. By locking the random seed, we guarantee that the shuffle is identical across all runs, establishing a stable baseline for our experiments. Once our data is split, the software lifecycle of a machine learning model follows a standard four-step design pattern: instantiation, fitting, prediction, and evaluation. During instantiation, we define our model's architecture and set its hyperparameters, such as selecting a linear regression model or a decision tree with a maximum depth of 5. During fitting, we call the model's training algorithm, passing the training features and training targets. This step runs the mathematical optimization, such as gradient descent, to solve for the model's parameters. During prediction, we pass the test features to the fitted model, which performs the forward mathematical calculations to output predicted values. Finally, during evaluation, we compare these predictions to the actual test targets using our evaluation metrics, validating the model's accuracy on unseen data. Transitioning to engineering design decisions, how we structure and organize this code determines whether our machine learning systems can be integrated into production environments. While Jupyter notebooks are popular for interactive exploration, they are poorly suited for production pipelines. Notebooks store state globally and allow cells to be executed out of order, which frequently leads to hidden state bugs and makes version control and automated testing virtually impossible. To build maintainable systems, engineers write modular Python scripts organized into clear functions and classes. We separate our code into distinct modules: one for data ingestion and cleaning, one for feature engineering, one for model training, and one for evaluation. This modular structure allows us to write unit tests for individual components, run our pipelines automatically using headless cron jobs or orchestration tools, and track changes reliably using version control systems. We also face critical decisions regarding data scaling and memory management. In production, we often process datasets that are too large to fit into a system's RAM. If you attempt to load a 50 gigabyte data file into memory on a server with 16 gigabytes of RAM, the operating system will crash with an out-of-memory error. To prevent these crashes, engineers use streaming and chunking. Instead of loading the entire file at once, we write generators that read the data in small, manageable batches. We also use memory-mapped file formats, such as Parquet or HDF5, which store data in a column-oriented, compressed format. Columnar storage allows our data pipelines to read only the specific columns required for a feature set, bypassing the rest of the file and drastically reducing RAM utilization and disk input-output bottlenecks. To see these practical steps in action, let us study a production case study of a marketing analytics platform. The platform's goal is to predict future customer sales based on historical advertising spend across television, radio, and social media channels. The engineering team builds a modular Python pipeline to execute this task. The first script reads the marketing transaction logs from a compressed Parquet file, extracting the advertising expenditures as the feature matrix X and the total sales revenue as the target vector Y. The pipeline then calls a partitioning module, which performs an 80-20 train test split, locking the random state with a seed of 42 to ensure reproducibility. Next, the training script instantiates a linear regression model. When the script calls the fit function on the training set, the underlying compiled C library performs a matrix multiplication to solve the normal equation, calculating the optimal parameter weights in a few milliseconds. The prediction module then runs the test features through the fitted model, generating predicted sales values. Finally, the evaluation module compares these predictions to the actual test sales, calculating a root mean squared error of 2.3, meaning the model's sales predictions deviate by an average of $2.30. The pipeline logs this metric to a centralized database and exports the trained model as a serialized file, ready to be served in production. Troubleshooting and debugging Python-based data pipelines requires a systematic approach to resolving memory constraints, randomness failures, and dimension mismatches. If your training pipeline crashes with an out-of-memory error, the first step is to profile your RAM usage. You can debug this by refactoring your data ingestion to use Pandas chunking parameters, or by transitioning from Pandas to lazy evaluation libraries like Polars or Dask, which construct computational graphs and process data in parallel streams rather than loading all variables into memory at once. Randomness failures occur when a pipeline produces varying results across runs, making it impossible to debug performance regressions. To debug randomness issues, you must audit your pipeline for any unseeded random processes. You must ensure that the random state is set not only in your train test split, but also in any downstream algorithms that rely on stochastic processes, such as gradient-boosted trees or neural network weight initializations. By setting the global seeds for NumberPy, Python's built-in random module, and any deep learning frameworks at the very top of your entry point script, you lock the mathematical entropy of your system, guaranteeing bitwise reproducible results. Dimension mismatch errors are another common pitfall, occurring when the shape of your feature matrices does not align with the expectations of the model's mathematical functions. For instance, if a model expects a two-dimensional matrix of shape n samples by one feature, and you pass a one-dimensional array of shape n samples, the dot product calculations will fail, throwing a value error. To debug dimension mismatches, engineers inspect the shape attribute of their arrays at each step of the pipeline. You can use reshaping functions to explicitly add dimensions, converting a flat vector into a column matrix. By implementing runtime assertion checks in your data validation layer that verify matrix shapes and data types before they are passed to the model, you can intercept dimension errors early, preventing pipeline crashes and ensuring the reliability of your machine learning software. To structure our machine learning pipelines professionally, we must look at the design patterns of scikit-learn. The library uses a uniform object-oriented interface based on three primary concepts: estimators, transformers, and predictors. An estimator is any object that can learn from data, and it implements the fit method. A transformer is an estimator that can modify the data, implementing the transform method, which is used for pre-processing steps like scaling or encoding. A predictor is an estimator that can make predictions, implementing the predict method, which is used for models. By using this uniform interface, scikit-learn allows us to chain multiple transformers and predictors together into a single pipeline object. The pipeline object acts as a container that encapsulates the entire workflow. When we call fit on a pipeline, it sequentially calls fit and transform on all pre-processing stages, and calls fit on the final model. When we call predict, it applies the transforms to the new data and passes it to the model. Encapsulating our workflow in a pipeline is an essential engineering practice because it mathematically prevents metric leakage, ensuring that our pre-processing statistics are computed exclusively on the training folds during cross-validation. We must also evaluate the security and scalability implications of model serialization. Once a model is trained, we must save its parameters to disk so it can be loaded for inference in our production services. The standard Python tool for serialization is the Pickle module, or the joblib library, which optimizes Pickle for large numerical arrays. However, unpickling serializations is a severe security risk. The Pickle format is executable, meaning that when you unpickle a file, the Python interpreter executes the instructions contained within it. If an attacker tampers with your model file or uploads a malicious pickle file, unpickling it can execute arbitrary shell commands on your server, compromising your infrastructure. To secure your systems, engineers restrict model loading to trusted sources, verify file hashes, or serialize models using non-executable formats like ONNX or JSON-based parameter exports, protecting production environments from remote code execution vulnerabilities. To write clean and error-free pipeline code in Python, we must master the distinction between the fit, transform, and fit_transform methods in scikit-learn. The fit method calculates the parameters of our transformation, such as the mean and standard deviation of a feature during standardization. The transform method applies these calculated parameters to the data, scaling it accordingly. The fit_transform method combines both steps into a single optimized operation. Crucially, we must only call fit or fit_transform on our training dataset. When preparing our test dataset, we must only call the transform method using the parameters calculated from the training set. Calling fit_transform on the test set is a severe coding error that calculates new parameters based on the test data, leaking information from our validation window into our predictions and completely invalidates our evaluation metrics. To manage dependencies and ensure reproducibility across different development and production environments, engineers use virtual environments. Python applications rely on a wide range of external libraries, and installing them globally on your system will eventually lead to dependency conflicts, commonly known as dependency hell, where one model requires version 1 of a library and another requires version 2. To prevent these conflicts, we use virtual environments, isolated directory trees that contain their own Python binaries and library installations. We use tools like pip paired with virtualenv or the Conda package manager. Conda is particularly popular in data science because it manages not only Python packages, but also binary system dependencies like GPU computing drivers and C libraries, ensuring that our execution environments are identical from our local workstations to our production Kubernetes clusters. To monitor these modular pipelines in production, engineers must implement structured logging and telemetry. Relying on simple print statements is a major pipeline failure, as prints are unstructured and difficult to search in centralized logging systems. Instead, we use Python's built-in logging module to generate structured JSON logs that record the timestamp, module name, log level, and a unique correlation ID for each prediction request. This correlation ID allows us to trace a user's transaction across multiple microservices, matching the features passed to the model with the resulting prediction and downstream metrics. By streaming these structured logs to centralized monitoring platforms like Elasticsearch or Prometheus, we can set up automated alerts for pipeline errors, track execution latencies, and debug failed inference requests in real time, ensuring the long-term reliability of our production machine learning services. Congratulations on completing this comprehensive exploration of the mathematical and conceptual foundations of machine learning. By staying through to the end, you have built a deep and structured mental model of the core pillars of our field. We have covered the unifying philosophy of statistical learning, the key learning paradigms of supervised, unsupervised, and reinforcement systems, and the critical mechanics of the bias-variance trade-off. We explored the geometric landscapes of linear algebra and vector spaces, the probabilistic models of uncertainty, and the statistical tools of hypothesis testing. We walked through the optimization engine of calculus and backpropagation, learned how to evaluate models reliably under class imbalance, and saw how to translate these abstract mathematical principles into robust, reproducible Python pipelines. You now possess the foundational engineering coordinates to navigate and design advanced machine learning architectures, transforming you from a developer who merely connects black boxes into an architect who understands how to build, optimize, and debug intelligent systems from the ground up.